So I'm going to talk, as Demetra said, about the in-kind process and how that relates to the AGN SC, and you have a bunch of interesting talks coming up, and I'll talk mostly from the perspective of the Observatory, as I work with the in-kind program team there, and also Greg Medeski, who is one of the in-kind program coordinators, is also participating in the meeting today. So please feel free to reach out to either me or Greg at any time. Oh. Okay, so what I'm going to go through is kind of the top level overview of what the in-kind program is, give you also a flavour of all the AGN in-kind contributions that we have in hand to date. I'll introduce the rest of the in-kind program coordination team and talk about how the contributions are tracked and managed. And then I'll talk very briefly about kind of what the future prospects or immediate prospects for AGN SC in the in-kind program is, and we'll conclude with the Q&A. So the in-kind program, as many of you know, was born out of the change in operations or funding model for the Rubin telescope, and that involved basically teams buying data rights essentially through in-kind contributions, and that can be to Rubin, the observatory and operations itself, as well as to the LSST science community. And so these have quite a diverse range and scope, and many of the management of the AGN SC, along with the other SCs, were part of the process in selecting and approving the contributions that were coming in, and we thank them for the immense effort that they've put in to generating this program and bringing it up to speed. So there's kind of 5 main flavors of contribution. There's the ones that go directly to the observatory and their offsets for processing or operations or software. We have telescope time contributions. We have international data access centers and also CPU processing. We have various data sets coming in. And then there's also software contributions. That's predominantly the largest type that is coming into the kind of science collaboration network from the in-kind program. Now in this list, you might have noticed that I've highlighted 4 of them, and that's not just because I missed off the first one by accident, but it's because those are the ones that I think you should see as potential connections to the AGN SC. So in terms of telescope time, essentially that provides access to various telescopes. I think we have about 8 countries contributing time on 16 telescopes ranging from 1 meter up to 10 meters. And this time will essentially be distributed to the US and Chilean community through Nuclei Lab. There's also transient target capability, which I think will be of interest to the AGN SC. In terms of IDAX and CPU, some of you have been involved with the LINK workshop that recently published a white paper. But in a similar way, there are resources within the in-kind program, and also, you know, access opportunities through the IDAX that may be of interest to your collaboration. So do keep an eye on them. Datasets often means kind of like value-added data sets with new data sets being brought in alongside the LSST data, and they will be of use to you in certain ways. Then, as you are probably most familiar with, software that's predominantly to do with infrastructure to enable you to perform the science that you want to do for your collaboration. So I just wanted to point out that these kind of these contributions are all also part of the PCW and be discussed further there. So I've just flagged up the sessions that are upcoming. There's a couple that I'll go through at the end of the talk as well. And I'll also kind of, I know you've had like your AGN SC roadmap talks yesterday, but I'll talk a little bit about kind of software contributions and what may be available to you in the near future. So this is a summary table of all the contributions that are affiliated with the AGN SC. And the ones that are in white are where the AGN SC is a primary recipient. That means that they are responsible effectively for the direction and the coordination of the effort that's coming in. There are a couple that are more grayed out, the top and bottom ones that are basically where AGN SC has been identified as one of the potential contributors. And I think in at least, well, I think in both of these cases, these are going predominantly to Noir Lab, but the AGN SC should be aware that these are contributions that are also kind of flagged for them. So the ones that are in bold here are the ones you're going to hear about after my talk. So I'm not going to go into those in more detail, but what you do see here is that you have a range, this range of type of contribution is reflected in your set of contributions. So predominantly they're these directable software development contributions, which basically means that they have some flexibility in terms of what they're delivering for the recipient to kind of tailor the output of the contribution towards their goals. And it involves a lot of interaction between the contributor and the recipient group. We have one targeted new complementary data set from Aprajita, and then there's these telescope time one, and also this survey, the near-infrared data fusion that's being led in the UK by Amanda Banerjee. So you see you have quite a rich set of contributions that are coming in, and then there may be prospects for more along the line. The last column here you see is what we call the Contribution Ipc. So I'm just going to talk about that a little bit more. So basically we have this in-kind program office that sits under the Rubin Operations Directorate. And our goal as a team is to help make the in-kind contributions successful. And for every contribution, there's kind of two flavors of IPC. We have the Contribution Ipc. So they are the kind of primary contact with the contribution lead, and we'll also interact with the recipient group on a contribution basis. We also have a program IPC, and a program is defined as like the institute or the country that's defined a package of work to the in-kind program to generate their data rights. And some of the interactions you may have with us will either be with your contribution IPC for specific contributions, or with the program IPC if it's a more programmatic activity or query. And that includes tracking and the current status checks that we're doing at the moment. So I realize there's a mixed audience here. We have some contributors, we have some of you who are very involved with the tracking and the receiving of the contributions. We may also have some of the program managers here. So I'm trying to make this talk good for everyone, but by definition that means I can't cover everything for everyone. But as I said, feel free to follow up with me after the talk. So our IPC team is all listed here. So we actually have Steve Margheim and Steve Ridgway, who are working on the telescope time and predominantly on the data sets. Actually, Steve Margheim is taking more of a lead on the telescope time as Steve Ridgway phases out. But they're both available to talk about those. And obviously, Steve Ridgway has done a lot of work in setting up all those. Knut Olsen also works partly with the data sets, but mostly with IDAX and computing resources. Myself and Greg working on the software development, and Phil Marshall, whose area is mostly with the Rubin recipients. So hopefully, putting mugshots of all of us up there have at least brought some of the names that you may have interacted with to life in some way. But I hope that you can interact with us either on Slack or directly, just so that you know who we are and what we're doing and where you can reach out for help. We also have great insight and advice from Bob and Phil, and also Heather Shaughnessy, who some of you may have been contacted for the data right holders list, which obviously also the management of the AGN SC also need to check the data right holders list to ensure their membership is up to date. So I'm going to talk now about kind of making and receiving these in-kind contributions, but I'm not going to go in, I don't have time to go into a lot of detail, but essentially a lot of this stuff has already been presented in various kind of community sessions. So this is actually, when you get the slides, you'll find the slides and recording linked to this PCW session last year, where we really went through this in a lot of detail. There's lots of information on the different types of contribution, and we also have a lot of Q&A arising from that session that we've tried to incorporate into a global FAQ that I will come to towards the end of the talk. We also have this rather large document called the Manual for In-Kind Contributors and Recipients, and and that's basically a living document that details the whole process. And we're currently revising it for this year. This was written around this time last year, so there's some updates we have to do, but you're always welcome to provide any feedback via the linked form, again, that you'll be able to access once you have the slides as a PDF. Within that manual, right at the end, there's an appendix, and what we try to do is distill kind of the main activities for both the leads and the recipients in terms of the process and when they need to take action. And for any of you contribution leads, I hope you realise that a lot of the responsibility or the onus of kicking things off is really up to the contribution lead, and you should embed and engage as much as you can, which I think you are all doing with your recipient leads, and then just check through this checklist to make sure that you're on track with things you need to do. Similarly, there's a checklist for recipients, and obviously what we've tried to do in the system is try to make the load on the recipient as little as we can, and hope that the IPC team can also help you with some of the tasks in management. And we're all kind of getting to speed with this program now, but if any of you involved in the reception of these contributions have any queries or questions, please just get in touch with how we can help you manage them better. So basically, as you know, some of these in-kind contributions have kicked off, and you'll be hearing about some of them shortly. But there's a basic process that they should follow, which I've tried to summarize in this slide. And it's mostly written in terms of like an annual cycle. So the first step would be, when you start an in-kind contribution, is that you write something called the work plan. And the work plan essentially takes the key information like objectives and milestones and puts them in a form with various other questions. And essentially, this is the document that basically you work towards with your recipients to achieve those goals and objectives. The process is that typically this should be written 2 to 3 months, and preferably not longer than 3 months before the start of the contribution for software. And that's really because if you start too early, you can find that by the time you start, things have actually changed in terms of, where the SC is in terms of their priorities and needs. So it should be quite close to the actual start date. And there's typically takes about a month to a couple of months just to go through all the kind of approval process, such that both you and the recipients and us in the IPC office are kind of happy with how the work plan is set. And then essentially, if we can get that finished about a month before you actually start, then you're all good to go. And the other critical part of this is that within the work plan, which is very much a top level overview of what you think the contribution is at that time, it also has a more detailed section where you can put in basically your actual planned work for the next 3 months. And then this will be followed up by quarterly updates. So there's 3 quarterly updates in a year. The schedule is shown in this table down here. And basically in that, you basically have the opportunity to report on the work that you've done so far in the previous quarter, and then lay out the work for the next quarter. And the goal again is to be, quite lightweight about this. We don't want you to have to spend lots of time writing lots and lots of text that the recipients also then have to spend a lot of time looking through, bullet points and highlighting key achievements is sufficient for these things. And it's just a way of monitoring, how you're doing and where the contribution is going. Then the final kind of quarterly update is actually replaced with what we call the annual evaluation. And this is a more holistic overview of what you've achieved over the year. So that gives you an opportunity to reflect on the work that you've done so far and the progress, but also for the recipients to see the same and see how it's fitting in with their plans. But also then to, it gives a way to interact between you and the recipients and the IPC team and where the contribution is going and how the future steps are going to be. So the basis of this annual evaluation is that we will basically ask you by the mid-September to submit the form that we'll share with you in a few weeks, and that will basically allow you to report on your work. We will then have a review stage for the recipient and also review it in the IPC team. And based on the comments that have come from that, we will then generate a report for the entire in-kind program for the Director of Operations, Blum, who will then take that forward to the resource board and the management board. Okay, so this is a more graphical calendar view of these kind of key points over the year. So obviously we're in 2020.
3 minutes.
Thank you. And there you see the kind of key times to do the quarterly updates. We're currently doing this thing called a status check, which is mostly a programmatic check, which many of you may not have come across because it's really with the program managers. But we're basically just checking the general commitment and deliverables and effort that's been committed to each of these contributions. And then this is the time period for the submission of the annual evaluation. And this is the period where we'll be kind of reviewing it. And then the cycle starts again at Q1 in December. So in terms of, that's kind of where we are. And there are things, as I said, that are already happening in the AGN SC. In terms of what's coming along, I think the main points are to attend the PCW if you can. We will be recording it. There will be also remote participation, and we have a session on the Thursday, the 11th at 3:30. That's MST time, where we'll basically go through the annual evaluation. A second part of that session is dedicated to the telescope time contribution. So if you want to find out more about how you might potentially access or even just get an overview of the telescope time resources that are available, the second half of our in-kind session will be devoted to that. But there's also another session that is being organized by the TVS collaboration on the day before, which is also about particularly follow-up facilities and opportunities in time domain astronomy that might be of relevance to several of you here as well. There will be another session on the IDAX and software and the connection to LINC. So as I mentioned, some of you have been involved with the LINC use cases. And this is really, again, looking at the resources that are available and trying to think for your particular science cases or science requirements, where these kind of access points or compute centers might be useful to help you achieve your scientific goals. The other thing I really wanted to highlight to you is that we also have this pool of general software development effort. This is basically effort that has been promised to Rubin, but can be deployed anywhere within Rubin or within the SCs. So it's really a development resource. There's lots of highly skilled developers as part of this. So in terms of your roadmap or your infrastructure roadmap, if you've identified gaps where you might need more effort that don't exist within the collaboration itself, this is an opportunity to perform either like small, targeted, highly skilled bits of coding, or it may be a longer term project that somehow ties in with perhaps your other in-kind, international in-kinds, as well as your, general effort from your SC community. So that's an opportunity for you to kind of fill the gap. So please do watch out for the general pool. And if any of you are interested in that, please just ping me or Greg a message after this talk, and we'll just make sure that we know about you and that we can keep you informed of the opportunities that we are going to announce in the next few weeks.
Okay, we should be done, are we?
Yeah, this is the last one. So I just wanted to say that we have kind of support also for you and for the recipient. So we're always available for individual consultations, and we are planning a session for best practice in software development, and also another one for managing and receiving software contributions. And I'll just leave up this slide while I take questions, which includes the links to the FAQs, our office hour booking, and also if you have any general queries, there's an address there that you can ping us on. Okay, thank you.
Okay, thank you, Aprajita. Okay, so we have a first question asked by Dragana. Dragana, do you want to ask it yourself? Okay, I'll do it. Well, she thanks you for the talk and the great overview, and says, could you please let us know, will there be soon another call for new in-kind proposals?
So the current status is that we want to get the current batch of accepted proposals up and running and running smoothly. So we want to make a success of what we have at the moment. So there's no current timeline for extensions or opening up to new calls, but we will let you know when that opportunity might arise again. But I don't think it won't be before spring next year.
Okay, thank you. Niel, next, please.
Thank you for the helpful review. I wanted to ask just a little bit more about these quarterly updates you described and who these will go to. Will these go to a committee of Rubin folks, or will these go to the science collaboration chairs or the science collaboration in-kind representatives? It would be helpful to have some connection with the science collaboration.
Yeah, so these will go to the in-kind contact that's being provided, which I think is Seb at the moment, but will be changing for you. And
I've been reviewing some of them, yeah.
So like I'm also a little bit behind in circulating all of those, so that may be why you haven't seen them. But effectively, we send it back to the contact, but you should feel free to distribute that to whoever you want within the collaboration, whether that's the chairs or the working group leads, however it works best for you. And then when you're happy with it, your in-kind contact can send it back to me with comments or approval or whatever you want to tell me about the contributions, and we'll log things that way. One thing that is actually I haven't been able to do yet, but I will be doing soon, is the ones where your secondary contact for. So predominantly these are going out only to the primary contacts, but the secondary contacts should still have access to everything that's being submitted. So once that's all ready, I will give you a notice of where you can access all that information, because you should also be feeding in to anything that arises from the secondary recipients, just so that, you know, the contributors know what your position is on those as well.
Great, thanks a lot.
No worries.
Maurizio?
I'm sorry, I couldn't unmute myself. No, mine was a trivial question. All the time that you were listing about the PCW and the session were in Eastern time, just to know that when to connect in case.
Yeah, so what I'll do is on the Slack, I'll put this list of sessions that are particularly related to the in-kinds, so that you can access them there. But you'll also, like when you have the PDF as well, each of those are linked. So you should be able to go directly to the PCW page and look at what that session is about in more detail.
But the time is mountain, right? Mountain standard time. So it's
sorry,
1 hour behind.
Yeah,
no, it's fine. It's 1 hour behind. So Maurizio, for us, it's -7.
Yeah, it's not the most European friendly time, shall we say.
That's fine. Thank you. So Gordon, we still have time for one question.
Yeah, thanks for the update and summary of how this works. I don't know if this is a question for you, but I think it's an important one to ask. I mean, I guess, you know, for me, the elephant in the room here is that receiving in-kind contributions is basically asking people to do work for free, right? And so I'm curious what the project, you know, thinks of that.
It's not work for free. It's work in exchange for data rights, right? I mean, that's why they're there.
No, I mean, I think I really mean that. I mean, no. So like, if I'm receiving the in-kind contribution,
oh, I see. As the
right, somebody is getting something, but not the one receiving anything, right?
Yeah, no, I totally. Yeah, sorry, I misunderstood when you framed the question. Yes, so indeed there is an overhead in terms of you receiving, you plural, receiving these contributions and how you manage them. How much time that takes is, I think, actually quite dependent on the individual relationship between the contribution leads and the recipient. And indeed, there is no model to give you something back for the time that you're spending on that. Partly that's because, in a way, what we wanted to do was try and enlarge the resources available to the science collaborations, and the kind of model was it would be very similar to someone who was just working in the collaboration, not necessarily for data rights, but providing some elements of say, your pipelines or the infrastructure, but they would still be kind of working with you to make something productive. So in a way, it was seen that this in-kind work would fit in with your general kind of processes for setting up the science that you want to do. Now I realize is a completely simplistic statement, and all these things have consequences in terms of people's time and resources that are available. And I don't have, and I know, I mean, we discussed, because I was at that time when this was set up, I was also a science collaboration chair, and we talked a huge amount about this and the load on the recipient. So all I can say is that we've tried our best to take out kind of the management aspects as much as we can, so that you can make it, you know, you don't have to worry about tracking stuff, because we're doing all that bit for you, that hopefully the work that you're doing is really the scientific direction to the contribution lead. And if there are ways that we can improve and make things more efficient for you, we're very happy to hear your feedback and try and enable that as much as we can. But I think you're right, it is an elephant in the room, and I think it is something we're conscious of, but it's also something we can't eliminate from the process, because really your assessment of
I'm sorry to interrupt, but we should move on to next speaker. So maybe move this to Slack.
Thanks, Aprajita.
Sorry.
No worries.
Really sorry.
No problem. Thank you.
So thank you. Thank you for the very interesting talk. And we are moving on to our next speaker, Bozena Czerny, who will talk us about emission line time delays from LSST AGN photometry. Bozena, please, all yours.
Okay, hello. Okay. Okay, I think. Can you hear the screen?
Yeah, we can see it.
Okay, it's right. So I will start with the program which we are developing, and this is our in-kind contribution from Poland to AGN collaboration. The co-authors are listed here. I have 2 slides of general introduction. I don't have to speak more about light echo studies because an excellent talk by Ami covered that quite well. In general, reverberation mapping of AGN is important for 2 reasons. First is this understanding of the structure of the flow close to the black hole, including broad line region, and then time delays can be also used to constrain parameters of cosmological models. And we are using light echo because the direct resolution of the flow is generally impossible. Only in the infrared 3 bright AGNs were resolved by gravity, and then Event Horizon Telescope resolved 2 sources, but those are low luminosity sources of different character. So broad emission line delays are studied since 50 years. The delay of lines were noticed already in 70s, and then it was proposed to use this time delay measurement for cosmology in 2011 by 2 groups. Errors are quite large, but we are making progress, and specifically listing the results from our group. We tried to do cosmology with time delays of H beta line. We had a sample of over 100 objects collected from the literature, and that caused problems. On the other hand, time delays in magnesium-2 were working quite nicely, and they could be combined with carbon-4 delays. So we have 78 measurements in magnesium-2 and 38 measurements in carbon-4. This is also mostly from literature. Some magnesium-2 time delays are ours. And those constraints can be combined with baryon acoustic oscillations and chronometer measurements of age, and that helps to constrain cosmology. So getting more delays from LSST would be really very important for those applications. But of course, here we deal with photometric redshift, not with spectroscopic redshifts, not with with photometric data, not with full spectra. And to determine the line delay is more complicated. Here you have an example of a source at redshift 2.5, overplotted with different colors, and this is a very good example to see the potential problems, because here we have Lyman alpha and carbon 4 line overlapping more or less in the same channel. So they are really messed up, and then magnesium 2 is only in the last Z channel, which is not very convenient for reverberation mapping. So we wrote, I guess, quite a complex software, which is now working, and I would like to present the details. So we have several parameters, input parameters in this software. First, we assume redshift of the source. Most examples are for 2.7 redshift, and this redshift is needed to determine which photometric channel we will use. Then we have to assume monochromatic luminosity, absolute luminosity of the source, because that is necessary to predict the expected time delay, which will be used in simulations. Then we need to assume AGN spectral properties, which are based on mean quasar spectra, but they can be, of course, modified. So we assume optical UV slope, we assume equivalence width of those lines, which delay will be measured. We include Fe2 pseudocontinuum, we include starlight. We have to parameterize response function for lines. We use Gaussian. We have to parameterize the AGN variability, and we do that through power spectrum that includes two frequency breaks, three slopes, and variability amplitude. And finally, we have to assume the position on the sky, which determines cadence. And we have here in the presentation 2 examples, one for main survey and one for deep drilling fields. So this is how our artificial spectrum looks like in the rest frame. So we have here all those 3 lines, carbon 4, magnesium 2, H beta. This wiggling here is starlight. So everything is really included. Now, if we go to the observed frame, then this spectrum overlaps with photometric channels, and we see that carbon 4 is more or less well situated in channel number 3. We can use safely channel number 4 for reference, and magnesium 2 is not very conveniently set. So in this choice of redshift, we will use carbon 4, which means channel 3 and channel 4 as a reference. So then we measure the amount of contamination of carbon 4 to this channel. We do that by calculating the same spectrum, but without carbon 4. You see now it disappeared. So then we calculate for each lines their relative contribution to each channel. I use numbers, not colors, but they go from U down. And this is for H beta, magnesium to carbon 4. So of course it depends strongly on the redshift. And we see the dominant contribution is from carbon 4 to channel number 3. And channel number 4 is safe to use as a reference. Then we created a single artificial light curve using T-Mercanic algorithm with exponentiation. This is an example. This covers some 30 years to be on the safe side. And then we calculate the second light curve, which is a convolution. This simulates the time delay. So it's based on Gaussian response function for lines, which we expect, and we assume the width of the Gaussian always as 0.1 of the time delay. This time delay comes from the absolute luminosity of the source assumed. And now from the position of the sky, we know how many visits we have during this 10 years. This is the example for the main survey, and this other case is for deep drilling fields. And this is the part which is quite complicated, sorry for that, but finally we construct the predicted channels 3 and 4 in our specific case, taking into account the contamination, potential contamination from emission lines, both for this photometric channel, which in principle should not be contaminated, but you never know, and then this channel, which we call spectroscopy, which contains the line, but can have also other contamination. And here also we include the random error related to the expected accuracy of photometry. And that is measured by the factor P. So that's quite complicated, but anyway, here you see an example of a channel which is channel 4, and then you see a channel which represents spectroscopy. They look similar, so plotted together, you see that they are slightly different because of this contamination by carbon 4 line, which is slightly delay with respect to photometry. Then computing time delay of those two lines, two light curves, would be quite complicated because they are very similar apart from this 12% contribution. So what we actually do is additionally we compare the channel which we name photometric with the channel containing emission line, but after subtraction of the channel, photometric channel with certain weight, which is arbitrarily chosen between 0.85 and 1.15 right now in the code, and we do 10 steps between those two values, and we optimize for the time delay. So we calculate the time delay between actually the difference and the photometric not contaminated channel. And then we calculate the time delay. Right now we have in the code 3 methods: ICCF, chi-square method with amplitude renormalization, and chi-square without such renormalization. We can include Javelin. We have experience, but it requires the change a bit of this code structure. And for every set of parameters, we run the code 100 times, just randomly, and then we calculate the mean time delay and the dispersion of this time delay, which measures the quality of the prediction. And now the results. The results, this is something which we do not yet fully understand. We need to do more tests. First, when we did the main survey prediction for low luminosity source, we see that obtained time delay is always below the time delay which was put into the system. There are some gaps, and gaps means that there is no suitable line to use in computations. Oh, sorry. That was partially due to the zero time delay dominating the time delay. So we decided to restrict the probed time delay to something which starts at 0.25 of the expected time delay. That helps a bit, but still it looks like we have a problem for low luminosity sources. Although at higher redshift it becomes better. If we take higher luminosity sources, then everything looks really quite fine for the main survey. I think I'm really satisfied, particularly at higher redshift. At redshift below 1, it looks like still we have a problem. Now, if we use low luminosity source, the one which was not really working with the main survey, we see that situation improves if we use the cadence from deep drilling field, although it's still not quite perfect. We are still systematically below, so even if we measure thousands of sources, we will under-predict the actual time delay. And then we did 2 very interesting experiments. We took deep drilling field, but not 10 years, but only 2 years. So the time delay at high redshift, of course, was not so well recovered, but the situation at lower redshift actually improved. When I go back, you see at low redshift with 10 years light curve, we are doing much worse than only with 2 years light curve. This probably has to do something with cadence and something with long-term trends. So it
3 minutes.
Okay, yes. It may suggest that actually in the case of deep drilling field, it will be better to cut the light curve even after 10 years into 1 or 2 years, and then calculate the time delay independently, at least for lower luminosity sources. We can try to study this in more detail. Anyway, we tried to do the same experiment with 1 year, and that was working quite well, but only for redshift below 0.5, and then the delay saturates because, you know, the light curve is not long enough to predict anything reasonable. But it's quite encouraging that after 1 year of deep drilling field, we can get delays for low luminosity sources, for redshifts up to 0.5, and for 2 years, we can go, I guess, for up to redshift 1, a bit more. We can try also higher luminosities. In that case, we didn't run this yet. So overall, we have to do more experiments now since this code is working, and of course we can share this code, although it's not so user-friendly yet. We should make some improvements to the code as well, because for the moment, the delay for carbon-4 is assumed to be the same as for magnesium-2 and H-beta, and this is not quite correct. Then the way how we subtract those 2 photometric curves to get the line excess better, this should be improved or changed. Then a response function for broadline region, as we now know from independent experiments, it should be changed from Gaussian to half Gaussian. Gaussian is not really representing well broadline region. And then in principle, we should include both time delays from the disk itself and line delays, but that would complicate the program quite considerably. So that cannot be do quite soon. On the other hand, we see from other experiments that it's really quite important. Thank you.
Thank you, Bozena. Perfect timing. Okay, so
I can stop sharing. I guess.
I see we have questions. Franz, you asked the question, but I think Keith replied to you. Are you okay with the reply?
Sure. I mean, Bozena in her final bullet point mentioned this as well, so it's fine.
Okay, so then we have Seb, please.
Yeah. Okay. So thanks, Bozena. And I want to. I mean, this is kind of the first comment that I want to make here on. I mean, Bozena showed exactly what they're doing, where they are at the moment. And this is, again, remember, this is an in-kind contribution to the entire science collaboration. So Bozena very clearly showed where they're currently working on and where maybe expertise, comments, input from all of you who are working on or are interested in the photometric reverberation mapping can actually help, right, and improve and shape this, this contribution. So I mean, I'm looking at the call, there are quite a number of people who are interested in that or have expertise, and be it with either simulated light curves on, well, including or not including continuum lags, etc. Please get in touch with Bozena. We'll discuss a little bit of how we can do that in the future, maybe better than we do at the moment. But this is exactly, I mean, you are supposed to shape it, because at the end, this is for us, for all of us. So if you have any comments, any suggestions for them, please get in touch.
Yeah, sure. I would be grateful for any suggestions, because some of those results are quite surprising.
Okay, Niel?
Yeah, thanks a lot, Bozena. So along the lines of what Seb just said, it would be helpful at some point to coordinate a bit on, you know, what language, computer language this is being written in, you know, when we can get like a preliminary version of the code to start looking at it. You know, we want to ensure that there's some level of documentation and commenting in the code so that this is a genuinely useful product to the science collaboration broadly. So hopefully there can be some interactions there in the coming months.
For the moment, we don't have yet the documentation, but we started to work with my collaborators on more user-friendly version, which will be based on input file without hidden parameters inside the code, which is the situation at present. So then the language of the code probably will not be that important, but it's actually Fortran. But you can always include that in Python code as a subroutine.
Okay, thanks.
Thank you. Maurizio?
Bozena, I was wondering, maybe you said that, but clearly it seems all the sources you're thinking on are relatively bright, even the faint one. So the AGN emission is dominating the source, and the stars are just a small nuisance there, right? Well,
I have the starlight included. So if you choose the source, which is really faint, you will see that in the starlight contribution. So that will smear, that will lower your level of variability, right?
Right. Now, I was wondering if in that case, one should work on the different image analysis light curves, which are, as Vincenzo shows, still a bit problematic.
Okay, Dragana, do you want to ask?
Yeah, thank you, Demetra. I was not sure that you asked my question. I'm with very poor internet, so I hope you hear me. Thank you very much, Bozena, for this nice presentation. And I also support Seb saying that we as a recipient and also other in-kind teams should all meet more regularly and discuss all these topics and share suggestions. And one just suggestion to Bozena's for the estimation of the light time lags. So we have been testing this as well for the photometric time lags, but using the solution Daniel formalism, and you can see the publication from this year, Yankov et al. And what we have shown basically, and this is something that is maybe worthwhile exploring, is that when you do when you combine the observed light curves with some of the non-parametric modeling tools, you actually were able to extract more accurate time lags, photometric time lags. So maybe this is some niche to explore further. Thanks.
I guess if I know a suitable code to do that, it's relatively easy to even include in computations, because you know, everything is sort of written in a form of blocks.
Yeah, well, that is a good idea. Yes, thank you very much. We should synergize all our efforts. Thanks.
Okay, we have some more questions, but we are almost out of time. So I suggest that we move the discussion to the Slack and move on to our next speaker. Thank you, Bozena, for your talk. So our next speaker is Mara Salvato with MPE photometric redshift for LSST detected AGN.
Yes, thanks. Can you hear and see?
Yes.
Yes, okay. So thank you for giving the opportunity to repeat my talk on the in-kind contribution. The title that was assigned to me was MP photometric redshift for LSST detected AGN. In reality, this confusion came out already another time. We are not proposing to compute the photosys for the AGN because I think that this is a community effort. But what we are actually interested in providing is a tool that can actually compute reliably photosys for AGN that LSST will detect. We definitely want to be involved in the computation as part of the SC, but we are not meant to compute it for all the sources. So we have 3 in-kind contributions. The first one, as I said, is the development of the software that is necessary for computing the reliable photometric redshifts. And we wanted to highlight again, as Seb was saying before, for Bozena contribution, it really is something meant to be discussed and developed within the SC. We provide the manpower, the expertise, and the will of work on it, but we should grow with the expertise and also the wishes of the team. We are not starting from scratch with our code. We are starting from Lfr. There is a reason for it. First of all, Lfr is a well-tested code. It is since 15 years reliably used for normal galaxies, not only AGNs. There are a lot of papers where the properties of the characteristic of the code is compared to other codes, and the capability, reliability is shown very clearly in those papers. It can also be used for stellar masses, the physical properties, not only photosys, and it also has the possibility to be used for a star and extragalactic source separation. It has been used in the last 15 years for AGNs. These are all the pencil beam surveys that have been using Lfr for the AGN computation, either by me or my students or people that I actually train in other collaboration. And again, the results were reliable. And the reason why to use Lfr is there are many more reasons. You can read them here. I'm not going to mention all. It is meant for the video recorded. Later, you can go back and check which were the important point. Here, what is important for me to highlight is that while at the beginning, the DM was considering to provide for the LSST sources only one photometric redshift, and this was done assuming that all the objects were galaxies. In the letter of recommendation that we all submitted, 3 just between Roberto and myself, we highlighted the point that you need to have more than one photosy application because it allows to identify peculiar objects, for example, and because different photosys have different characteristics. And Lfr has been actually approved to be one of the 6 that DM is going to apply to all the sources, regardless on which type of objects they are. So because Lfr has the possibility to run simultaneously through 3 independent libraries, one of the stellar, 1 Galactic, and 1 AGN, in the moment in which DM is going to run Lfr, if our AGN modulus is developed, it can be ingested there, and automatically they can also provide a first order photosys, assuming for each object to be an AGN. And then by the discrepancy with the photosys, assuming by the object being a galaxy, we can identify peculiar objects. This is perfectly fitting the motivation and connecting our work to the roadmap. One of the goals in the roadmap for AGN is to identify AGNs in different ways. And one way is indeed just look at every source and see how different photosys are coming, assuming an AGN template or a galaxy template. And by the discrepancies, we are going to highlight interesting objects for our work. The work done on AGN so far in Lfr has been done using the modulus of the galaxy. So I was telling at the beginning that 3 modules are already working. However, the only one that is really developed is the one working for galaxies. The others, for quasars and stars, simply take templates and fit them at a certain redshift with minimal chi-square. There is no possibility to have a prior. There is no correction for IgM. There is no possibility to do anything, essentially no possibility to add extinction, because all these objects were assumed to be quasar, no issues with extinctions. Instead, in the galaxy part, you have the priors, you have a different extinction, you have the emission lines on the templates, and so on. So what the level 0 of our work is going to be cloning the galaxy model and making it valid also for the quasar part, adding some features that are necessary for the AGN, like, for example, having not only extinction from the galaxy, but also extinction from the obscuration coming from the AGN itself. Again, these are just examples of things that needed to be improved in the modulo of AGN for computing photosys. So we put manpower for working on this. One thing that is also interesting to say is that when we submitted the in-kind contribution project, we were supposed to work alone. We were in agreement with Olivier Hilbert and Stéphane Arnoux, which are those that created Lfr in the first place, so they were aware of our effort and they were happy we were developing the AGN part. However, meantime, Olivier and Stéphane became active in the ASC, and they are proposing and improving also the galaxy part of Lfr. So we are in close contact to make sure that our AGN modulo is going to be still consistent with the general Lfr. The second contribution is again manpower to offer to the entire AGN SC for understanding how to improve photosys for AGN. Having a reliable code is not sufficient. There are plenty of activities that need to be done in order to have reliable works. We needed to to solve some problem in the templates that are not really perfect. We needed to verify which UV slopes are ideal for the template. We needed to understand how to account for variability, because LSST will have issues with variability, and so on. I apologize, I'm working from home because I'm sick and my cat wants to take part to the meeting. I just want to give you below some example of applications. So here you see how in the latest work of Eurosita IFEDS, we were selecting the templates, taking into account the color plot of AGN known with spectroscopic redshift, and see how the templates were behaving. And you see that overall templates are following the behavior, the up and down of the actual AGNs, but there are clear cases, so like here in the W1 minus W2, where a lot of sources are not represented by the templates that we are using. So we needed to understand these discrepancies. I think that in this part here, in the lower part, this is even more clear that there is something that is amiss. This is a recent work that we are doing for Erosita ERAS1, where we are getting a better handle of templates, and we needed to check if these templates are going to be good also for LSST. So I'm testing on the AGN X-ray detected, but of course we are going to do something also for the optically selected AGN by LSST. Another example, in our templates, we only have one slope, which is based on this paper, but in reality, the dispersion is very high in the slope that you can have. And so the idea is to test whether there is a better slope for improving on our results. This is a complicated plot that shows how photoses are influenced by the variability in the photometry. And so the quality, accuracy, and fraction of outliers is much smaller when you take photometry from catalogs that have photometry gathered closer in time, rather than photometry randomized, so taken at different times, so G in one time, R in another time. So we need to understand what is the best way to take advantage of the variability in order to get reliable photometry achievement. And all this is work that we have to prioritize within SC and work together in how to move forward. Another thing that we needed to work on is the PDZ. As you probably know, we don't want to have only a redshift estimate. We also want to have the probability distribution function. It is already known since many years that in SCD fitting, the probability distribution function is underestimated. So we consider, overestimated, sorry, we are sure to be right even when we are clearly wrong. And so we needed to have probability distribution function that are more realistic. And here you have a comparison between a probability distribution function for an object done with SCD fitting and with machine learning. So the machine learning, we think, as a PDZ that is more reliable. So we needed to understand how to carry on this feature also in SCD fitting. So another point we were already discussing before, that I've seen today, we are going to have talks on merging near-infrared photometry together to the LSST photometry. This indeed is an important point. As you know here, we are showing the quality of spec Z minus photoses for AGNs using with or without the near-infrared photometry. And you clearly see that with near-infrared photometry, you have good results. And without the near-infrared photometry, you have an excess of high redshift objects. We know that with the use of the U-band, we create low redshift objects that otherwise will be put at high redshift. So we needed to test also which are the essential bands. We know, for example, that in the templates that we are using after W2, so 4.5 micron, the templates are very unstable. And if you use W3 and W4 in the low redshift regime, this will screw the quality of your fit. But if you're working at very high redshift, W3 and W4, rest frame will be something the near infrared, so the photometry that will be reliable. So essentially what I am saying is that we needed to create in the use of our code a lot of if this is happening, then do this. If this is happening, then do this. And so the idea is really testing which are the various possibilities and then having like a decision tree, like a handmade machine learning, reduce the parameter space of the solution and get reliable results. And all these I'm really counted to do within the SC. The third contribution is the easy one, so where you can consider me your ambassador for eROSITA sources. We are going to provide for LSST sources they match with the eROSITA data, providing the information that are needed, possibly also the light curve for the brightest objects. We were supposed to start the work in January 2022, so this year we actually hired a postdoc that unfortunately meantime found a more stable job outside academia, and so we lost our perfect guy and we have to start from scratch. That's why since yesterday, I believe, or 2 days ago, the call for a postdoc with me developing the software and working on LSST and maybe eROSITA science is actually open. And I would be glad if you can spread the voice, and if you know somebody that has the skills that are needed for a job, please don't hesitate to put a person in contact with me. I am done, Demetra, with my contributions. The only thing that I have left are 3 plots that shows other work we are doing in terms of photosys that can be relevant to LSST photosys for AGN. And I do not know whether you want to discuss this now or in the discussion later. Up to you.
Okay, I think if you start showing them, we'll see what questions come out.
Okay, so how much time I may be able to
you
fast?
You still have 3 minutes and 35
Okay, but
seconds.
then it's enough. So if you remember yesterday, I was asking details about the aperture photometry. And we have already people working on photosys via machine learning that instead of using model flux or imaging from a deep learning, they actually using the aperture photometry that various surveys are starting to provide. And using machine learning on these fluxes in the aperture, they're actually having decent, reasonable results. The first example that I want to show you is this one. I just taken, or my student has taken the photosys from the legacy survey DR9 for all the objects that we know are AGN from IFED's eROSITA. And what you see is that for the extended sources or objects below Redshift 1, the photosys are actually very reliable. They were not knowing that these were AGN, simply the training sample was for extended sources. But then you see that for the point like it is a mess because the training sample was not accounting for quasars essentially. A similar work is done in the DNNZ. They again use aperture photometry, using the various aperture photometry fluxes that are given in IPSuprIncome. And then you can see how this result, although they were not trained for AGN, but they had a larger sample up to Redshift 3 or 4, they started to be comparable in accuracy and fraction of outliers with the SED fitting. So there is really a lot of good work coming on. And so we are starting to experiment in our team. And here what you see. We started to use the DR9, but training exclusively only on AGN, so not on galaxies. This is the training sample, this is the validation sample, and this is a blind test. And what you see is that compared to the SED fitting is that despite the dispersion being large and maybe the fraction of outliers still not being nice, what you have is that there is no this large amount of sources at high redshift that are actually wrong just because the bands were not sufficient for identifying the right redshifts. So I think that probably combining SED fitting and machine learning, it is the way to go. And the final plot is actually one project to do with the desk, and this we can discuss later in the discussion time. Thank you.
Okay, thank you, Mara. So first of all, we have a question by Ilsang saying, is the discrepancy between the template and the data seen in white colors suggesting that dust extinction of AGN itself need to be improved? It's in the chat here if you want to read it.
Yeah. So I agree. Dust can be one of the issues, and I agree this is one of the items that we need to understand. That dust can definitely be one of the points. I totally agree. Okay. Again, the point. I mean, if I want to iterate more, the code as it is now has only one extinction for the galaxy and not for the AGN component. And indeed, one of the points we wanted to have is the additional contribution from the extinction due to around the AGN. And this maybe will explain some of the results.
Okay, I actually meant to ask something about this slide myself, because I was wondering, out of curiosity, if there's any, in which direction you're going to move to represent, to include more and more AGN type. Sorry.
No, no, very good question. So we try to explain it in our papers. The risk is that because you have a very limited number of photometry points, you create more degeneracy than other when you have too many templates. And so the idea is really to be well aware of the type of AGN that you are looking at and use a limited representative library. This plot here was just showing all the templates that we have, and see that despite we have many, a lot of points are still out of the curves that you see. So there is a lot of work really done in selecting the right templates.
I see. Thanks. Maurizio?
I was just curious when you were mentioning the different slopes in the spectra, which I sort of missed. So you're saying that you have to include a variety of slope to better represent your sample.
So what I'm saying is that all this work is done in an empirical way. We are using templates of AGN essentially that were observed by Sloan, even at high redshift, but because they were observed at the high redshift, they got absorbed by the AGN. If you want to use these templates for representing quasar at redshift 3, 4, 5, and so on, because Lfr by default has a correction for AGN, I needed to add back what was expected to be the slope in the UV part in order to allow the Lfr to absorb a certain amount of it. And we have seen that the results change slightly depending on which slope I assume. When I assume this slope, I use just the sharp value that Scott et al. Was giving in 2004, but actually it should be 0.56 plus minus a lot. And so we needed to see whether there is a better slopes that represent better all the objects, or maybe we need to have 3 different slopes that I do not know yet.
Okay, I just wanted to mention that I think Olena Torbaniuk in Naples was doing some work on that, so maybe we can get in touch to see if it
Absolutely. Helps. It's really, so this work is really meant, I'm putting on the table all what the option that, all the issues that I know are existing, and we can one by one tackle them, set a priority, and work together on them. It's really meant in serving the SC and not as me doing the work for myself.
Okay, Roberto, next.
Oh, cool. Thanks. A really good talk, really exciting work. So in the previous slide about the same thing Ilsan was asking. So in principle, right, it would be hard for dust to create the blue excess sources, right? The ones that are too blue in Ys, unless it's so much dust that you're seeing the host galaxy. Do you think that's the case? That it's just the host galaxy coming up?
It cannot be the host galaxy, because here you are redshift 2, 3, and 4, and at that point the galaxy should practically not visible. It should be really, these are all AGN. The dots that I'm showing are really all AGN. So you see here the part below are the galaxy dominated objects, redshift up to redshift 1.5, and these are the point-like sources. So it could also be you know, that the photometry we're using here was the DR9 photometry, and we know that the DR9 photometry had some issue. It has actually combined with the I band, which is coming from another survey. So, sorry, this is W1, W2, so it's still related to DR9. Sorry, sorry, I use here DR8. DR9 came out after I did the work. We know that there is a difference in photometry between DR8 and DR9, and it could be that with DR9, some of the dots disappear. It's always matter also checking the photometry, not only the templates.
Yeah, it would be that would be inclined. It could also be some kind of emission lines, but it seems too scattered to be systematic.
Yeah, it is too scattered. It could also be, you know, blending issues, for example. It can be that there is maybe a background issue. So this is also some can be some problem.
Cool, thanks.
No problem.
Okay, I think it's time for a break now. We need to shrink it a little, so we started a little later, so let's meet at 5 to noon Eastern. Thank you, Mara, for giving this talk, and I hope you get well soon. Thank you, Bozena and Aprajita, and see you in 7 minutes. Please be on time, or we propagate the delay. Thanks.
Thanks.
Lost power, so our chair has lost power, so I'm going to take over for a little bit here and introduce the next set of speakers. We have 2 more speakers talking about their groups in kind contributions. The next one is Angelika Kovacevic talking about the CIRSAG directable software in kind contributions. And she's going to report on the construction of a time domain pipeline for periodicity search. So
thank you, Mr. Chairman, for a nice introduction. Hello, my name is Angelika Kovacevic, and I am lead of CIRSAG in-kind directable software contribution. On behalf of our team, I will present technical report on construction of time domain periodicity mining pipeline for AGN and stellar light curves, which can complement and help other LSST pipelines in frequency domain. We thank you to organizers of AGN summer meeting for giving us the opportunity to present this report. First of all, please let me introduce the CIRSAG team. Based on our in-kind contribution, we are supposed to have data right holders with equivalent worth of 6 PIs. The project and program managers are Luka Popovic and Dragana Ilic. Effective staff consists beside Angelika Kovacevic, Viktor Radovic, and supported by advisors Rachel Stirit, Mladen Nikolic, Jan Rongli, and Xiaon He. We organized 2 sub-teams with the 2 grant supports from LSST Enabling Science. And from this team, George Savic, Isidora Yankov, and Iva Hajdinjak participated in Data Challenge. Tomorrow, Wei Zhangyu and George Savic will present AGN Data Challenge. The second TVS Kickstarter team is in cooperation with Croatia Participation Group, co-led by Sasha Simic and Tomislav Jurkic. The goal of the time domain periodicity pipeline is to find periodic signals in LSST time series data with emphasis on observations of AGN and stars. And here we will advertise the excellent talk which will be given tomorrow by Maria Carisi on binary supermassive black holes. Pipeline is original in that it combines multiple wavelengths using our original 2D hybrid method and deep learning of light curves. Extracted curve periodic characteristics are pipeline output. Here we can see the general structure, and we will visit today 2 computational utilities, the framework for deep learning of light curves and the framework of periodicity detection. And we will see the 3rd point as well, and that is the pilot massive exploitation of the pipeline at the AI platform. So let us first look at the conditional neural process unit, the unit related to the deep learning. We need deep learning unit as some wavelets demand regularly cadenced light curve, and sometimes deep learning models are described as being like the brain, but one analogy given by Niel Lawrence might be useful to think of them as being similar to football table or pinball machine. So as the ball falls through the machine, each layer of players or pins can be taught as different layer of neurons. And on this side, you can see our conditional neural process machine table. This is the forward pass through this unit. And we will now take a much more detailed look in our GitHub repository. Just a moment, please. Which can be seen here, and we will see here the main architecture. So each pair of the input points is passed through the multi-layer perceptron in order to get a lower encoding of these input points, and then these lower encodings are aggregated in more general representation, which is then fed into another MPL, which is called decoder, alongside with the target inputs, in order to get the mean and the variance of the model. Of the predicted distribution of target points. Also, we refactored the code in order to have the data classes and collate custom functions. We can have also metrics, different metrics, log probability loss and MISI. Then we are training the model in separate unit, save the model, and also calculate the train and validation losses. And finally, we can upload the trained model later whenever we want into prediction unit, and then we can make the plots of train and test light curves, and also to save all other data in JSON files. So actually, the CNPs can be seen. The CNPs can be seen actually as meta learners. So because of that, we could use them on different collection of objects. And on the right side, you can see the modeling of NGC 5548 H beta light curve after training our CNP on 100 SSN light curves. And also we trained CNP on 40,000 ZTF light curves, kindly provided by Paula Sanchez-Saez. And you can see here some results. And also CNP has been successfully used by Yankov et al. As modeling tool of LCs as a part of their automated procedure for LSST photoreverberation mapping. And now we would like to say that we run CNP large-scale simulation using ZTF sets of 120,000 light curves for different configurations of some parameters, for example, for different batch sizes, hardware configuration, training epochs. We obtained that GPUs speed up workload at least 10 times. And now we are proceeding to the second computational unit that is related to the periodicity detection based on our 2D hybrid method depicted on the right side, which actually input original or deep learned light curves. Then it correlates matrices of wave transforms of original or modeled light curves, and we ended up with correlated periodic signals presented in both curves. So the axis are actually accounts for periods in the light curves. Of course, we could autocorrelate wavelet matrix so that both axes will account for periods in one light curve. What's more, the 2D map can be integrated along any of axes in order to get periodogram-like version. And our pipeline can be easily combined with classical or any other type of periodicity detection. And we are now going to see a notebook with scientific case supplied by CPG team. The CPG team, led by Fatovic, detected this very interesting periodically variable quasar candidate. You can see here original data with overlying oscillation curve, and on the right side you can see the folded light curves of the object, and they detected period of 278 days. And here we will actually apply this data set has many interesting properties, so we can use to showcase our pipeline using two types of wavelets, WZ, suitable for original non-homogeneous cadence light curve, and superlets for homogeneous cadence. And as we are looking for superlets as well, we will need actually to build deep Gaussian models of input light curve per advice of our statistical supervisors, that it is useful to have both deep Gaussians and also conditional neural processes together. So we built actually deep Gaussians with 2 layers, or with added latent variable layer, or combine them with Keras neural dense layers. And what we can see here is actually 2 layers deep Gaussian process However, when we add latent variable layer, we can see more structure. And after 5,000 samples of deep Gaussian process, we end up with this highly structured model, which we will use for pellets. And now we are passing to see how it does look like a combination of the Keras neural network and deep Gaussian processes. And we are passing to detect periods using WZ for original, irregular cadence, and superlets. Superlets are actually the sets of wavelets with fixed central frequency, but the range of the cycles. And what's more, importantly, we intend to use them for fast transients events, for detection periodic fast transient events. After we are now proceeding to use firstly WZ method, testing that we have original data, setting input parameters, invoking WZ. We need 45 seconds for this, and then autocorrelating the metrics, and we end up with 2D hybrid method map with two prominent correlation clusters on the main diagonal. And we can integrate above image, and we can get two prominent peaks, one of the correlation 1, and we can estimate the error using a method similar to Schwarzberg-Czerny by measuring 25th and 75th quantile above the full width half maximum of the peak. And we end up with the period of 278.4 days with upper and lower errors, and for the secondary peak. As for the significance of detected period, we can use the two approaches, the faster approach, which are using just shuffling of the original light curve, and then we are numbering the times that the peak power of the period in original data is greater than in mock data. And we have done it just for 100 mock light curves for demonstration purposes. And we can plot the histogram of these correlation peaks found in mock light curves. And we can see that we do not have peaks at correlation 1. So according to this approach, we detected this period with significance of 100%. Also, we can use, according to the advice of our statistical supervisor, slower bootstrap method, which actually bootstrapping the original light curve, and then we actually detect peaks. And in the histogram of detected peaks in mock light curves, we fit generalized extrema probability density function, from which, for given significance level, we can estimate associated confidence level. So we can use either IID or moving block bootstrap. Here is the moving block bootstrap method. And here you can see how it does look like generalized extreme value distribution probability density function. And you can see here in the blue color histogram of the period peaks in mock light curves, and you can see GV, fitted GV PDF, and you can see here the estimates of the significance. And we can see that our peak in original data is above the significance of 0.1. We are now proceeding to superlets. We intend them for fast transient events. However, here are they for just demonstration purposes. We are using the modeled light curves, latent variable layer plus 2 deep GPs. And please, you can see here wiggles, which are consequence of inducing latent variable layer. We are setting the frequency grid, transforming this frequency grid into the scales, invoking the superlet. We can see actually the original superlet metrics, autocorrelating the metrics, and we end up with 2D hybrid method map, which topology is almost the same as in the case of WZ method. And when we integrate above the image, we got 2 peaks at about 1 year with correlation 1 and at the correlation 0.78, 77, the period of 288 days. Using the same estimate measure of errors, we got this periods. We excluded this 1 year period because it can be related to some other consequences. And using the faster approach, the significance in this case is about 95% because we have the 5 peaks at the level and larger of 0.78. And using GeV, we actually also end up with somewhere lower significance, about 0.12. Going back, we are coming to the third point, and that besides pipeline as open access, we also offer massive exploitation of our pipeline at our AI platform based on requests by LSST community. The compute service consists of temporary data storage with over 250 terabytes as a realization of joint project between CERSAC and CPG, while AI platform consists, of 4 NVIDIA servers with 120,000 nodes. And for example, the most demanding task of calculation is statistical significance of detected period. And for example, using 100 mock light curves, will need more than 1.5 hours at personal computing station configured like this. However, at the AI platform, we will need just several minutes. We also performed pilot tests.
About 3 minutes.
Thank you. We also performed pilot tests of massive exploitation of our pipeline on AI platform using 1,000 artificial light constructed light curves constructed for selected OPSIM cadences and with different injected periods. On the left is heat map for injected period of 150 days, representing relative errors of detected periods for different level of amplitudes of signal on y-axis and LSST cadences. On the right is the same, but for more sterile-like case of injected period of 10 days. And finally, your feedback matters. Please contact Dragana Ilic, our program manager, and me, Angelika Kovacevic, contribution lead. Also, you are more than welcome to fill in our Google form in order that we can communicate and meet each other. And also, our special thanks go to LSST, CC, AGN, and TVS SCs, and special thanks to International Program Coordinator, Aprajita Verma, then to CSC contacts, Sebastian Höning, Paul Coppi, Federica Bianco, and Rachel Street. Of course, we are grateful to our colleagues from Croatia and Poland in-kind teams led by Lovro Palavresra and Bozena Czerny. Also, we are thankful to LSST Enabling Science and Hastings-Simons Foundation. So thank you so much for your time and attention.
Great, thank you. Demetra will take over now.
Yeah, sorry. Thank you, Angelika. So any questions? Okay, Maria, please.
Hi, I have a couple of questions. One, I wasn't clear on what type of periodicity you are sensitive to, whether this is restricted only to sinusoidal periodicity or more generic. That's the first one. You can answer that and I can.
Okay, thank you so much. In order, because we are using the wavelets, WZ wavelets are actually using the projection on the trigonometric basis function. However, superlets doesn't use them. Also, continuous wavelet transform doesn't use them. And we are in cooperation with our statistical advisor that we use some other wavelets which are not in this, in conventional basis. So I could say that our method can also search both for sinusoidal periods and also for non-sinusoidal periods due to the characteristics of the wavelets. And that is the main difference between the Fourier methods and wavelet methods, because the Fourier actually assumes fitting or projections on trigonometric basis function. Thank you so much for your excellent question.
Thanks. And the second question I had, you showed this example of the periodic candidate, and you demonstrated the calculation of the false alarm probability with simulations with bootstrapping.
Yes.
Is that does that take into account that quasars have correlated stochastic variability?
Excellent question. The main reason why we are advised by our supervisor to use the bootstrap method, I will, if I have time, just to go back to the notebook, just to the section of the significance. So in order, if we are actually using the slower approach, as it is suggested by Johnson et al., by shuffling light curve, we will destroy correlations. However, using the bootstrap method, and specifically which bootstrap? Moving block bootstrap. The moving block bootstrap will not destroy if exists any correlation within the light curve Y, because it is using the block. However, if we are using the, for example, IID bootstrap method, it will destroy any type of correlation in the light curve. So we are actually offering to potential users to have all of these combinations of the significance in order, if they are not, how to say, sure about the correlation levels in the light curves. So because of this, we have several, how to say, possibilities. And for the moving blue, for these bootstrap methods, we are using the statistical recombinator affiliated package, which is really, really good. So in this sense, we are accounting, we are taking care in the case that the light curve will have some correlation. And because of this, we demonstrated in this notebook the moving block bootstrap method. Besides just shuffling, which will destroy correlation. Thank you.
Thank you.
Okay, Maurizio?
I just didn't understand, do you need more computing power for running your GPU? So is here some help from the collaboration needed?
Just a moment, please. I will go back. So actually, at this level, we can run our pipeline on any type of IDAC, and we can run our pipeline in order, for example, if users have agreement with IDAC in Croatia, we can run them. So at this level, we can actually say that it can be okay. But we do not know what will happen in 5 years, of course, because the technology is speeding up. So what we are doing, we are offering to potential users, they can use our pipeline on, how to say, their own. But if they would like that we also run our pipeline on their data, we can do it on this machine.
Thanks.
Thanks.
Okay, I don't see other questions, and we can continue on Slack anyway. So thank you, Angelica. Sorry I missed part of your talk.
Thank you so much.
Let's move to next speaker then, who I believe is Andrea Grazian on behalf of Angela Bongiorno, who couldn't join us for good reasons today. So Andrea, are you here?
Yes. So
okay.
Let me share the screen. So let me. Okay. So this is the slide moving.
Yeah, but it's not presentation mode yet.
Not in presentation mode?
No.
No.
No? Okay.
Let me check.
Now I do.
Okay, I will start. So thank you very much. So I will describe the in-kind contribution of the Italian team working on AGN. So the aim of the in-kind contribution is to provide a simulated catalog and images for AGN and their host galaxies for the Rubin LSST survey, with particular emphasis on IZ objects. The lead of this in-kind contribution is Angela Bongiorno, and the team is listed here. So I'm the co-lead with Angela Bongiorno. We have different members with data rights, divided in staff, postdoc, and PhD. A 2-year postdoc fully dedicated to LSST simulation will start in October this year. And then we have a number of collaborators without that right that will help us on our activities. And the names are listed here. This is a schematic view of our in-kind contribution. So basically, we will generate 3 mock catalogs, one for galaxies using EGG, one for stars using Trilegal, and we will generate a AGN mock catalog using 2 different recipes. Then this mock catalog will be merged, and simulated images for LSST will be provided at different epoch, simulated different epoch of the LSST survey, using the official tools by LSST. And also we decide to provide also simulated Euclid images. Then we will use these simulated images to build a realistic catalog using the LSST official tools for photometric analysis. And then we will compare the output catalog with the input catalog in order to provide the difference and to have some validation of the code. Sorry. Okay. So the work plan has been divided in 4 main work packages. So the first work package will create the mock catalogs for star galaxies and AGN. And we include also the AGN variability, as I will show later. The second work packages will use those, will provide the scientific validation of the mock catalogs, and using the log S luminosity function or standard scaling relation. The third work package will simulate the images using in all the LSST bands and also in Euclid in different epoch of the survey. And the fourth work package will build the catalogs using the simulated images, using the photometric tools that have been provided by the LSST collaboration. So this is the list of deliverables of the in-kind contribution. So we'll release to the LSST community the mock catalogs for Star Galaxy and AGN, the simulated images, both LSST and Euclid. We release the extracted catalog from the simulated images, and we provide also the documentation, and also we provide some validation of all these deliverables that we provide. This is a timeline, a preliminary timeline of the project. So we will start officially in October this year, and the project will last for 2 years. And we will follow different steps of definition of the code, so production of the simulated catalogs and images, validation, and releases. And this is shown by this timeline here. There are also other add-on which are not included in the in-kind contribution, but it could be nice to follow up in the future. For example, we can use the images to test different tools for photometric analysis to extract the photometry in different images. And then so we can compare different photometric tools. We can test whether the usage of high resolution special images, for example, the one from Euclid, can be used to improve the photometric analysis of the LSST photometry, for example, using high special resolution priors in the photometric analysis. And another project that could be interesting is to test different techniques to classify the AGN, for example, using machine learning technique, as Vincenzo discussed yesterday. And of course, our team will not, this is not part of the in-kind contribution, but we would like to follow up these items if we have time, and the product of our in-kind, so the mock catalogs and simulated images, will be important in order to do all these, to follow up all these tests. Of course, the scientific motivation of our in-kind contribution can be summarized by these 4 open questions for the next decades, which is what is the contribution of the census of the supermassive black hole from the peak of the black hole activity of redshift 2 to the cosmic dawn? What is the seed of the supermassive black hole that we see at high redshift? What are the feeding and feedback of the supermassive black hole toward their host galaxies and toward the large-scale structure? And what is the contribution of AGN to the hydrogen reionization? And of course, we think that LSST can give a substantial contribution to solve or to give important answer to this question. Now I'm going into the details of the code. So we will start from the mock catalog, generating the mock catalog of galaxies. We will use EGG, which is an empirical tool. So EGG will start from the stellar mass function divided by generate redshift, stellar mass, and the classification for each galaxy. Then attach to each galaxy physical properties, for example, star formation rate and dust, temperature of the dust, infrared luminosity, and morphology, divided by bulge, contribution, and disk, and colors of the different components. And then the code will generate the panchromatic LCD for each galaxy. And so we will have a catalog with and then it is also able to reproduce the position of each galaxy, reproducing the two-point correlation function of the galaxies. And so with this code, we will have a catalog of galaxies with position and redshift and physical properties. Then we will use we have used Trilegal to generate a mock catalog of stars. So Trilegal is a population synthesis code for stellar photometry. So the code is able to generate a list of the stars with different magnitude in different filters at a given position in the galaxy. So as a test, we generate a catalog of stars in 1 square degrees at high galactic latitude, just to test the code. For the AGN catalog, which is the core of our in-kind contribution, we follow 2 different approaches. So the first one is based on the continuity equation. So the continuity equation described in the paper by Shang in 2013 ensures that the supermassive black hole is accrete in tandem with the stellar mass of the host galaxies. That the supermassive black hole that the population are following the Sultan argument, and then there is a continuous evolution of the black hole mass function and AGN luminosity function without breaks or jumps. And there will be a talk by Hao Fu tomorrow, where all this method will be described in details. The second approach is an empirical approach. So we will start from each galaxy produced by egg. So we'll start from redshift, stellar mass, and star formation rate. We divided using the specific star formation rate in different classes of starbust, main sequence, quiescent, and we extract for each galaxy an efficiency of black hole accretion rate following IRD 2019. In particular, IRD in 2019 provided for different classes of starbust, main sequence, or quiescent galaxies, and different redshift, the probability distribution function for the black hole, for the efficiency of black hole accretion rate, which is basically the ratio between the luminosity in X-ray luminosity of the AGN and the stellar mass of the host galaxies. And all those curves are normalized. So basically, we extract from the M star of the galaxy luminosity and X-ray luminosity for the object. Then we assign the variability and we convert the X-ray luminosity into UV band luminosity following Lusso, and we associate to each galaxy an extinction and a column density of neutral hydrogen following Vito. Then we can, using those parameters, we can assign to each AGN a template, an SCD, for example, from Salvato, Polletta, or Temple, and assign an AGN absorption from Inoue, and then convert the SCD into fluxes using the filter curves of LSST and Euclid. And so in this way, we will have a catalog, a mock catalog with the M star and star formation rate of the host galaxy, the morphology of the galaxy, and the properties of the AGN, and all the apparent magnitude in the LSST Euclid bands, which is the sum of the fluxes of the AGN and the host galaxies. For the synthetic, for variability, we use the dump the random walk model, as Vincenzo and other talks described yesterday very well. So basically, starting from the input parameter, for example, the volumetric luminosity, the black hole mass, and the magnitude and redshift, we are able to simulate the variability. Of course, we have to decide the cadence and the depth of the images in order to reproduce better the variability. And here we are working with Maurizio Paolillo and Vincenzo Petracca in order to iron out all these details in detail. To validate the mock catalogs, we will use, of course, log-N-log-S, so number counts, UV luminosity function in UV and X-ray, angular and spatial clustering, two-point correlation function of galaxy and AGN, and scalar relation, for example, the black hole and star relation, or the distribution of the black hole accretion, the efficiency of black hole accretion rate, and all. If you want, you can propose other validation tests. All suggestions are welcome. The current status of the activities. So the working group 1 has already produced a catalog of galaxy, AGN, and stars using the empirical relation. And we are currently analyzing the 2 recipes for the AGN mock catalog. We already produced a first simulated images of 40 square arc minute in the all 6 LSST filter and 1 Euclid band using SkyMaker. So now the working group 3 is working in order to update the recipes.
So then there are 3 minutes.
Just close to the end. The working group is updating recipes in order to use the LSS software tools in order to produce the simulated images. And the validation of the catalog will start as soon as we have a more stable recipes. So here we show some result. So this is the preliminary image for in 6 different LSST band and 1 Euclid band for 1 year cadence and the final survey of LSST after 10 years. So the green dot here mark the position of the AGN that we simulated the AGN. And here zoom in for the bands, and here is a zoom on 3 different quasar at different redshift, and you notice that the object is dropping, so drop out in the UG and R band. So basically, it's at redshift 3, 4, and 5. Okay, so our group is open to collaboration. So if you want to collaborate or have some add some feedback or have some information from us, please contact me or Angela Bongiorno. And here are the email of me and Angela. And it's worth stressing here that in order to train and prepare the software tools to rapidly exploit the real SST data, it's important to start right now to work on the simulated LSST and Euclid possible catalogs and images. So our work is important to prepare the tools for real data. And there is an open postdoc position in Rome to work with me and Angela Bongiorno on this topic. So here you can see the details. You can see the QR code, and the deadline is the end of September. So I'm finished and ready to answer the question. Thank you very much.
Thank you, Andrea. We have a question from Franz. Franz asks, how easy will it be to update prescriptions? For instance, if we find 1 year from now that variability is a function of black hole mass or accretion rate scales somewhat differently than current prescription, is the code being set up in a way that will not require too much manual tweaking? It's in the chat if you want to read it yourself.
So at the moment, we didn't insert the variability in our simple pipeline, and at the moment, our pipeline is a collection of big single scripts that are running in cascade. So and the variability is not present in our pipeline at the moment. So the idea is to restructure all these all the pipeline in a Python script, and of course, since the Python script will be organized in modules, it will be quite easy to implement another recipes if, for example, from 1 year from now, we will have another tools or another recipes or other ingredients for variability. So if you have suggestion for example, for variability, you can send an email to me, Angela Bongiorno, or interact with Vincenzo Petracca and Maurizio Paolillo, who are basically the key guy for the variability of AGN.
Okay, thank you. Bozena?
If I understand correctly, at some stage you can have the information that, let's say, in 1 square degree of the sky, whatever, you will have AGNs, so many AGNs of each mass and Eddington ratio. Is that correct? Because this is exactly what I need for our program. Because our program calculates whatever, but assuming practically black hole mass and Eddington ratio. And we do not have the information how many black hole masses, 10 to 9 or 10 to what statistically we will have from LSST. And this is necessary if we want to calculate the success rate, overall success rate in determining time delays. So I understand that I can get this from you, right? The information.
Yes, yes. We will provide a catalog of AGN in, for example, in different areas. So basically, you can have for a given area and for a given recipient of AGN, a different magnitude and with different black hole masses and luminosities. And of course, those are based on empirical recipes. So that if they are wrong, our catalog is wrong. But since we will try to use state-of-the-art empirical relation in order to build this mock-up.
So I understand I should write to you to know more details, right?
Yes.
Thank you.
Yes. Bye.
Okay, so if there are no more questions, thanks again, Andrea. And we switch to our next speaker, who is Fanzo, talking about multi-wavelength data and spectral energy distributions in the deep training fields.
Okay, just one moment.
Sure, take your time.
Can I see the screen well?
Yes.
Okay, great. So today I'm going to talk about the multi-wavelength data and the spectral energy distribution in the LSST deep drilling fields. And as you may already know, there are currently 5 chosen LSST deep drilling fields: the Cosmos, WCDFS, ELISS1, and the XMM LSS fields. And these 4 are the original 4 deep drilling fields. And in the March of this year, the Euclid Deep Field South was added to the 5th deep drilling field. And currently, the original 4 deep drilling fields have very extensive multi-wavelength coverage from X-ray to infrared and to radio. But the EDFS currently is far behind the 4 original ones in terms of the multi-wavelength data preparations. So in this presentation, I'm going to mainly focus on these 4 deep drilling fields. And So first, I will begin with briefly summarizing the representative multi-wavelength data sets in the LSST deep-drilling fields. And the first one is Cosmos, which is a very famous field. And this figure shows the multi-wavelength coverage in the Cosmos field. And the Cosmos 2020 catalog is the most up-to-date compilations of the UV to mid-infrared photometry in the Cosmos field. And as you can see, it covers the NUV band down to species channel 4. And besides the UV to mid-infrared photometry, we already have some X-ray coverage like Chandra Cosmos Selective Survey and far-infrared coverage from PEP and Hermes surveys and radio from VLA Cosmos, etc. And these are just some representative ones. And I haven't listed some other surveys like XMM Cosmos. And also, I want to highlight that the Cosmos has HST images, and we also have JWST images in the central region. So it will provide very high resolution images, and we will have morphological information for sources in Cosmos, and this may be helpful for some studies. And so overall, Cosmos is a very good field, and it also has very good photometric redshift measurements and well-cataloged stellar mass and star formation rate measurements from the SCD feeding from both the galaxy perspective, like Cosmos 2020, and also from AGN perspective, from like in several independent articles. So that's for Cosmos, and I'm sure this will be a very useful field for many kinds of scientific analysis in the future. And for the other three fields, WCTFS, ELISS1, and XMM LSS, we have parallel efforts devoted to the multi-wavelength data preparations in these three fields. And in this table, I'm summarizing some representative data sets in these three fields. And we can see that we also have X-ray surveys from XMM surfs, and also several UV to optical surveys and infrared surveys like Deep Drill and some other surveys down far infrared. And the UV to infrared photometry catalog are already available in Nyland et al. In preparation and Zhou et al. 2021. And we also have radio coverage from like Atlas and Mighty surveys. And again, these only lists the most important surveys, and there are also some surveys like, for example, WCTFS contain the good field, so it will have like small but deeper surveys that are not listed here. And we also have some Veil survey, which is not in the central part of the deep drilling field, is also not listed here. But this table summarizes the most important ones. And besides the photometry, we also have good photometric redshift measurements in these three fields. And here I'm comparing the photometric redshift with the spectroscopy redshift in the WCTFS field. And you can see that they are generally in good quality. And we also have refined photometric redshifts for broadline AGN from Niel et al. 2021. And so overall, these four LSST deep drilling fields now have very good photometry and also photometric redshifts. So, and as I already mentioned, the Cosmos field has very good stellar mass and star formation rate catalogs. But to prepare for the future science, we also want to do the SCD cataloging in these three fields. So in the next slides, I'm going to report our recent efforts in fitting the SCDs in these three fields, and it's not only for AGNs, it's also for galaxies. In total, it contains 3 million SCDs, and I'm going to begin with a very basic introduction of SCDs. So the multi-wavelength SCDs contain the imprints of all the physical processes in galaxies. And in this figure, you can see that for the same source, it shows different properties in different wavelengths. And that's because the emission of a galaxy in different wavelengths is usually dominated by different physical processes. Like in the X-ray, it's usually dominated by AGNs, and in UV to optical, it's usually dominated by young stars or AGN if present. And in near infrared, is from intermediate age to old stars, and in down to far infrared is mainly from dust emission, etc. So ideally, by fitting the SCDs of the galaxies, we can get the most important parameters of these galaxies, and this all, of course, including the AGNs residing in the center of these galaxies. So, so that's why we want to do our SCD fitting to get the galaxy properties. And the first thing we need to do is to do the source classification, and we classify sources into 4 categories: stars, AGN candidates, bursting or quenching galaxies, and normal galaxies. And in this presentation, I'm only going to focus on the selection of AGN candidates. And we use 3 different methods: X-ray, mid-infrared, and SCD methods to do the selection. And currently the radial selection is ongoing, but I'm not going to talk about the radial selection in this presentation. And I'm going to talk about these 3 methods, and I'm going to take the WCFS as a representative example for the 3 deep drilling fields. So the first, about the X-ray AGN selection, we rely on the XMM SURF survey, and this survey provides us with 50 kilosecond XMM Newton exposure, and it contains 10,000 AGNs in total in these 3 fields. And you can see that this figure shows the XMM Newton image in WCFS taken from Niel et al. 2021. And we have lots of point sources here, and in most cases they are X-ray AGNs, and this is how we select the AGNs. And we also select AGNs through the mid-infrared colors. And we know that the basic idea is that the mid-infrared emission of AGN is generally power low and redder compared to the galaxy emission. And we have these mid-infrared wedges to mimic the mid-infrared emission of AGNs. And basically, we select the AGNs located within these wedges as mid-infrared AGNs. And in these figures, I'm also showing the X-ray AGNs with the mid-infrared wedges, and you can see that most of the X-ray AGNs are also residing in the mid-infrared wedges. So that's for the X-ray and mid-infrared AGN selection, and these 2 are the standard ways to select AGNs in deep surveys. And we also want to try to select AGNs through their SCDs. So this figure showed an example SCD fitting, and we have these blue points, which are our observed photometry. And I want to highlight that we also include the X-ray data point here. And so the first step is to use a normal galaxy model to fit the SCD, and the best fit model is shown as the cyan dashed line here. And you can see that it cannot explain the X-ray excess, and also it cannot explain well the overall AGN shape, though although it's a little bit harder to see. And we then add an AGN component and we do the fitting, and the best fit model will become this thick gray line. And you can see that the thick gray line is much better in explaining the overall SCD, and it also we also decompose the overall SCD as an AGN component and a Galaxy component. So in this case, we can see that if a source shows if the fitting gets greatly improved after an AGN component, then we can say that it's an AGN candidate. And more quantitatively, we use a parameter called delta BIC to quantify the improvement. And as delta BIC increases, we say that there is more evidence supporting that the AGN, the source is an AGN from the SCD fitting perspective. And in this figure, I'm showing the stacked X-ray signals from the sources as delta BIC increases. And also in this figure, I'm showing that as delta BIC increases, how the mid-infrared colors of these sources distribute. And you can see that as delta BIC increases, that means the SCD favors that this source is an AGN. That we found that the X-ray signal get increased, and also it converges to the mid-infrared wedges. So that means the SCD selection is working, but we want to be more careful. We want to know the purity and completeness of our AGN candidates. And we also want to select more reliable SCD AGNs. So that's why we do the calibration of our SCD AGN selection. And the good thing of WSKFS is that it contains a small transient deep field south field, and this field has the deepest X-ray image ever taken. So basically, we assume that the transient sources in this field are the transient AGNs in this field are both complete and pure, and we apply the same SCD selection to this field using the wide field photometry, and compare our SCD AGN candidates with the transient sources. And here is the Venn diagram showing the results. And we can see that they generally have limited overlap between the X-ray transient AGNs and our SCD AGN candidates. So we can see that lots of X-ray AGNs are not identified as our candidates, but that's acceptable because that explains why we need the 7 microsecond transient exposure. But the more striking problem is that lots of our SCD AGN candidates are also not selected as transient AGNs, and this means that our candidates are highly contaminated by normal galaxies. So this is problematic, and in this figure, I'm showing that as we increase the delta BIC threshold, which means that we are becoming increasingly stricter in selecting SCD AGNs, the purity increases and the completeness decreases, and that's as we expect. And we set a purity threshold, like we set the purity threshold at like this level, and we want to select. We adjust our selection criteria to make sure that the purity reaches this level, and in this way we can construct a reliable SCD AGN selection criteria. And here is the result. By calibrating the criteria we get, we found that most of our reliable SCD AGNs are indeed X-ray AGNs, and the purity is 76%. And you can see that the number of true AGNs within these SCD AGNs only decreased by like a factor of 2 from 58 to 26. And then we apply the same criterion to the whole WSKFS field to select the
3 minutes.
Okay, great. To select reliable SCD AGNs, and we can see that most of the reliable SCD AGNs are actually also identified by X-rays or mid-infrared methods. So that means the SCD selection can hardly select more AGNs, more reliable AGNs missed by the other methods. So that's for the AGN selection. And I want to highlight that our SCD fitting also returned the stellar mass and star formation rate measurements for both pure galaxies and also AGN host galaxies. And this will be our main output. And in this figure, I'm comparing our stellar mass and star formation rate measurements with other measurements to justify our reliability. And generally, you can see that they agree with zero difference line. And similarly, this is also a similar figure, justifying that. And I want to highlight that we have released our data, and I will refer you to two data release websites. One is XMM Surfs, and this website includes X-ray catalogs and multi-wavelength photometry and photometric redshifts provided by the Penn State XMM Surfs team and some relevant papers in these deep drilling fields. And we also have the nodal repository, which is dedicated to release the SCD feeding results, including, of course, the catalogs and also the decomposed SCD models, and also some the compiled photometric catalogs. And if you are interested, you can check these two websites for more details. And I will stay here as both a summary and future prospects for the LSST deep drilling fields. And I will be happy to take any questions you have. Thank you.
Thank you, Fan. Thank you very much. Well, while we wait for questions, I would like to ask one myself. You mentioned radio coverage, radio catalogs. Did you actually use them to some extent? By the way, apologies because I mean to read your paper, but I haven't done it yet. So,
sorry, can I say that again?
I mean, I asked if you used the radio catalogs that you mentioned.
No, well, not really in this work, but we are trying to select radio AGNs. But in our SCD feeding, we are not using the radio catalogs.
Yeah, okay, I saw that you are not using them in the SCD. I was wondering if you were using them in some other work. Okay, yeah. Thank you. Franz?
Hi, Fan. So actually one interesting task, I guess, would be to basically remove or put at much higher level the X-ray limits to kind of simulate what we'll see outside of the DDFs, and then understand, if we're going to have a higher galaxy contamination fraction from that subset of things. Does that make sense?
Yeah, that sounds a good idea. Yeah, thanks for that. I think it's a good way to a good point to consider. Yeah.
It could be just either reject them all, don't include the X-ray information altogether, or include it but only at a higher level, and basically simulate what you do with Aprajita, or even with nothing in the regions where Aprajita doesn't have public coverage. Right. So we will kind of have a better understanding of what we think we're going to get. That would be useful.
Yeah, I agree. Yeah, thank you.
Okay, I don't see any other questions, not even in the Slack channel, and we can ask some later maybe. So I think this is a good time to take our group picture. I'd like to say two things. First of all, thanks again to the speakers of the previous section. And also for those who haven't sent their slides to Niel yet, please do it so you can share them as soon as possible. Okay, now we are ready for our next speaker, who is Raphael Shirley, talking about joint photometry from Vera Rubin Observatory optical and VISTA near-infrared imaging.
Hello, everybody. Can everybody see the screen?
Yes.
Yeah. So thank you for the introduction. It's a pleasure to talk to everyone. So I'm Raphael. I work at the University of Southampton in the United Kingdom, and I'm working mainly with Manda Banerjee, who's also at Southampton, and also Carlos Gonzalez Fernandez and Richard McMahon at the Institute of Astronomy in Cambridge. And yeah, as was said, I'm presenting work performing joint photometry on Vera Rubin optical data with VISTA near-infrared data. And this is part of the UK in-kind contribution. So essentially the idea is we're taking this data set, which is historically involved with the United Kingdom, this VISTA, various different VISTA data sets, and we're trying to sort of present them to the LSST science community in the form that is most useful to LSST scientists, and that's in general. So Manda's work is largely on AGN, but it's a general data set for the whole community. So although we are possibly targeted towards AGN just because of our own work, it is hopefully a general data set. So VISTA, I'm sure many of you are aware, the Visible and Infrared Survey Telescope for Astronomy. It's a 4-meter telescope at Paranal. It's about a 10-hour drive from Cerro Pachón, where Rubin is. 0.339 arc-second pixels on the VRCam camera. It's got a 1.65 square degree field of view. Crucially, it has been taking images with the Z, Y, J, H, and KS near infrared filters. So specifically VRCam, it's a Vista infrared camera, is a picture of it here with the filters there compared to the WIFCam and 2MASS and previous near infrared cameras. So, you know, the key additional data sets are going to be these J, H, and KS filters going beyond the LSST optical. And whilst it's true that the J and the H filters in particular will at some time hopefully be superseded over a large part of the wide, fast, deep survey by Euclid, the KS filter will be sort of, I think, over a lot of the LSST sky will be the only KS data for a large part of the LSST survey. And of course, at the start of LSST operations, that will also be true for J and H. So with possible Euclid delays and the general timeline anyway, particularly at the start of operations, I think this will be a sort of key near infrared data set for doing Rubin science. So why are the extra bands useful? Of course, because possibly it's fair to say most importantly, they're going to contribute to photometric redshift accuracy. So it's a paper from 2017 by Gomez et al. This is based on cross-matched UGRIS and YJHK data. It's showing, you know, improvements in accuracy you're getting. So we're currently looking at sort of investigating how that constraining power is a function of the near infrared depth. Obviously, we're going to have much deeper LSST imaging. So it's sort of we're starting to work on understanding at what point, you know, Vista is still contributing useful information to these photo-Z measurements. And here's sort of another image. This is from Amanda Banerjee's 2015 paper combining VHS. So this is this wide area Vista survey, the Vista Hemisphere survey. I'll explain all the different surveys in more detail shortly. But using that shallower Vista data, which again is going to cover most of the LSST sky, with DES data, and just showing how that deeper optical data, you know, lots of those detections are detected in the Vista imaging at low signal to noise. So, and as we go to lower and lower signal to noise, we're still getting peaks, and they're real objects that with Vista alone you wouldn't be confident in, but with the objects being confirmed in LSST, there is information there that can be used for science, I think. And again, another image from the same paper, just showing how the number counts by using this effectively forced photometry from the deeper optical data. You can essentially take the number counts deeper and sort of push the previous Vista imaging further while still providing useful information with the optical catalogs. So here's, as I said, is an overview of the Vista surveys. So I think that crucially we're looking at 3 surveys mainly: the VHS Vista Hemisphere survey. That's this sort of not very nice shade of green on this image, and that's covering the whole of the southern sky effectively. So going to plus I think about 2 degrees in general, and that's got a sort of huge overlap with the LSST wide, fast, deep survey. And as I said, you know, that is for large parts of the survey time, that's going to be the only near infrared data available. The other 2 surveys are the Viking survey in pink here, less wide and slightly deeper, and the video survey, it's been mentioned before a few times, in red. These are some smaller, I think three deep fields in particular, which I'll describe their positions later, and some sort of key details here. So the Viking survey is going to 21.2 in KS, VHS going to 20, and video going to 23.5. Yeah, there's more information there. You can read in more detail if you get the slides later, perhaps. Here's another figure. This is from previous work I did, combining optical and near-infrared and actually mid-infrared data across Herschel fields. So this is not the whole of the southern sky, but it's kind of representative of these three VISTA fields that we've been looking at. So what I'm showing here is depth essentially on the y-axis against the wavelength or band on the x-axis. And these violin plots are showing the distribution of depths on the sky. So you can see, for instance, if you look at the J band, there's kind of 3 peaks in this distribution, and that's broadly due to the video deepest, Viking, intermediate, and VHS coverage there. And on the optical, we see the main peak is from DES data, I think, and then the Hyper-SU prime cam deeper here, and Pan-STARRS at the top. But obviously these are the bulk of the area is all coming down here. And this is just showing, this is actually a starburst galaxy relevant to Herschel science, but you're possibly giving you some idea at different redshifts of where these different near-infrared bands are going to be corresponding to the optical depths that we're hoping to see. So a technical detail here, the actual processing that we're performing. We're using the LSST science pipelines to perform the force photometry. So the idea is that we produce VISTA catalogs in exactly the same format as the eventual LSST catalogs. We're just essentially adding bands in. So we're producing with this, the LSST science pipelines, we're going through every step as will be done for LSST, but we're not performing the very early steps of VISTA processing. That's just because a lot of effort went into producing the CASU pipelines. This is the Cambridge Astronomy Survey Unit. So all the dark, flat bias correction has already been performed, but every step beyond that is performed by the LSST science pipelines. So that means warping and co-adding. This is pixel matched imaging. That means for every LSST pixel, we will produce a VISTA pixel where available. And that sort of one-to-one matching means that there's a slight disjoint between the native pixel scaling in Rubin or Hyper-SU prime cam is our sort of precursor data set. And VISTA will obviously be oversampled, and you can see there with the before and after, we are oversampling. I think we had some issues with that at start, I think to do with the noise layer, but I think we fixed all those issues and we sort of understand exactly how that's working. But that does mean lots of any image algorithms that depend on pixel space, all this VISTA imaging will be available on the same pixel space. And in theory, that means algorithms can be quite easily extended on the imaging as well as the catalogs. And then of course we're performing photometry, and this sort of crucial aspect of the LSST science pipelines of detected in any band, measured in every band. And that's sort of crucial for our force photometry, because it both means that these very deep faint objects in LSST will all get measurements in VISTA, regardless of whether or not there's a VISTA detection. And also for unusual redder objects, conceivably there will be a small number of objects, even with the difference in depth, where we have a red object detected in VISTA, and we can then of course force that position to the LSST imaging. The VISTA imaging for bright objects will also contribute to the deblending. So some of you may be familiar with the Scarlet deblender, but that again, extra color information can help with deblending of bright objects. And we're aiming to perform all the same measurements that will be done on the LSST imaging. So at present, that's aperture photometry, convolved aperture photometry, C model fluxes and Cron fluxes. Although I'm actually under the impression there that C model fluxes are being deprecated and replaced with this Gaussian mixture model fluxes. But anyway, we're keeping the science pipelines up to date, such that sort of when this run is done, as I say, it should be identical to the main public LSST releases. And as I mentioned previously, the main precursor data sets, or what we're testing all our software on, is Hyper-SU prime cam. So the first tests we were doing with PDR2, we've now had PDR3. Here I'm just showing the fields. The top northern fields don't overlap with VISTA at all, but these two large wide area fields have got significant coverage going up to about +2 degrees. And this crucial in green here down at the bottom, this SXDS field has been a crucial test field for us. But in general, this is, I think it's 730 square degrees overlap area. will be available shortly. As I said, we've done previous runs on the Hypersphere PrimeCam PDR2 data, which is publicly available with certain issues, but particularly in the SXDS field, this deep field, we do have the test data already available, and we actually contributed that to the AGN data challenge work. So we're very keen for people to start looking at these precursor data sets, and we do hope to have the full PDR3 to a 700 square degree overlap performed in the next months. So as I mentioned, this SXDS field is sort of key test field for us. It's actually an important test field for Vista because it's covered by both the VHS wide surveys and video and Viking, and that allows us to do lots of comparisons between all these data sets, which has been very useful for testing. And as I said, this is the key test data set that we've run the pipelines on many times and is already available. So if you're interested in this field in particular, please do contact us and I can get the data sent to you. And here's just a sort of another image of the full overlap with PDR3. The blue here is VHS again, the green is Viking, and the darker areas are the video deep fields. So yeah, we've got these essentially these two large areas here that we're processing at the moment. And a key part of the work has been quality control. So obviously, if we want these data sets to be useful, we want to make sure they're on the same photometric solution as previous Vista data sets. So yeah, we've put a lot of work into producing significant diagnostic and plots, comparing. So here I'm comparing the R pipeline with the LSST science pipelines against previous S extractor catalogs, and just showing that we're getting, you know, median offsets and scatter as we'd expect them to be. And this again comparing VHS to the same band compared to previous catalogs, and it's just sort of making sure we understand where there are slight differences, possibly in how it deals with saturated pixels, that we're understanding all those effects, and of course comparing back to the Hypersphere PrimeCam original measurements. These are both performed with the LSST science pipelines. This is just checking, sort of sanity check, just checking we're getting very similar measurements there, and of course astrometry. It's just to sort of reassure people that a large part of the work we've been doing over the last 2 years has been, as I said, quality control, making sure the data is clean, and that the flags are working, things like that, and that we understand it. I think it's been mentioned a few times, a lot of AGN scientists are used to using SDSS and not perhaps used to the data products that are coming out of the LSST science pipelines. So you know, I think that our data set can be useful there, checking the quality of the measurements compared to previous pipelines and understanding the differences where there are differences. So now we're moving on to more scientific tests. So here I'm just highlighting, this is Ken Duncan's work on photometric redshifts that was previously done using cross matches between Hypersphere PrimeCam and Vista, and some SED fitting done by Kasia Majek. These are actually my previous collaborators, and they've started to look at our data sets and just comparing to, as I said, yeah, work that was done previously using cross matches, both as a sanity check and both just checking the quality of the data, particularly, as I said, these low signal to noise measurements where we believe this new pipeline will provide information that wouldn't have been there with previous cross matches. And we're moving on to using these data sets on PhD projects, and very much interested in community involvement. So if this data set sounds interesting to you, yeah, please get in touch. Would like to just
3 minutes.
Okay, just briefly mention this the new quasar SED model from Matthew Temple, and just another sort of scientific test. We're looking into using this for producing photometric redshifts for high redshift quasar selection. And just briefly, I'll show you some example images. This is a cluster at redshift 1.8, and just showing how the JHKS imaging can provide other information. Obviously, the resolution is slightly lower pixel scale, but you know that those extra red bands are giving you more information. And I've got a few examples of an extremely red object at redshift 2.5, and we're seeing it's not showing up or very faint in the Hypersphere PrimeCam bands, but then we are catching it in Vista Y and then seeing it in the JHKS bands. Another redshift 6 quasar, again showing how this is only really showing up in Hypersphere PrimeCam Z, but we're also capturing it in Vista Z and Vista Y, and a Lyman break galaxy between redshift 6.5 and 7.5. This is from one of Rebecca Bowler's high redshift candidates, and just showing how we are just picking it up in Vista Y and Vista J. And again, I think that's just giving you an idea of the difference in the imaging pixel scale, and yeah, showing how this imaging is already possibly useful. Another example here, some AGN host galaxies. Again, just showing how the JHKS bands are contributing to SED modeling, and particularly how that's crucial for the obscured quasar template here, and this other example in the sort of how you're getting the dust template is to some extent contributing to these JHKS bands. So the data is all being served publicly. QServe is the LSST table formats we're currently ingesting it into, and the UK and the main Rubin Science platform and the UK Rubin Science platform, all the data we hope to make available there. And just very briefly, I'd like to mention that as part of the requirements for in-kind contributions, all the code is public. We're very keen to get other eyes on this code, so please have a look. There's two main repositories, the OBS Vista package and the LSST Vista Fusion package. And yeah, I think that's a good time to wrap up, really, just saying we're producing aperture mapped photometry from Rubin, UGRIZI and Vista ZY-JHKS, in addition to all the other photometry measurements. Generation 2, that's a term referring to the LSST science pipelines. Those catalogs are already available on the Vista Science Archive, and we're moving on to the Gen 3. This is the latest LSST science pipelines. That rerun is currently underway. Yeah, the SXDS prototype has been used in the AGN data challenge already and is publicly available. And yeah, we're working towards having everything in place, so all these data sets are available at the start of operations, and with all the code public, so it can be modified by anyone if they wish to. I think, yeah, that's more or less the end.
Okay, thank you very much for your talk. So any questions? Niel, please go ahead.
Hi, thank you. Clearly, this will be a very valuable resource. I guess I wanted to ask a little bit about the technical details of the aperture matched photometry with your methodology. In our work on the deep drilling fields, we used Tractor, and that seemed to work pretty well in our experience. I guess I wanted to ask if you've ever done a sort of direct comparison with Tractor-based photometry versus your methodology, and what the strengths and weaknesses of the two methods relative to each other are.
We haven't directly compared with Tractor. I think, of course, one of the key advantages of our method is that we're forcing in both directions. Mm-hmm. So particularly for the rare red objects, that's an advantage of our method. I think the other key issue is, of course, with Tractor, you're assuming a morphology, I think it's fair to say.
Yes, yes.
So where there's actually differences in the morphology in the near infrared and optical, there obviously our method will be able to pick that up. So I think that's probably the main advantage we have there. Yeah. Okay.
It could be very helpful sometime to since Tractor catalogs are available in for example XMM LSS, just it'd be interesting to play with those and just see what the ups and downs are. So we can hopefully converge on something everybody agrees upon. But thanks
absolutely.
a lot.
I'll look into that. I will do that. Yeah.
Vincenzo.
Hi, Lfr. Thank you for the great talk. I have just a more technical question related to the possibility to use the LSST pipeline with Vista data. How much difficult it is to create an observation package, because we wanted to create it somehow for the cameras as well, but there is no detailed documentation on how to create it.
Right. So I used the example of OBS Anycam developed by James Mullaney. So he was, I think, one of the first people outside of the sort of core data management team to develop an OBS package for another instrument. He developed it for the GO2 instrument, these some smaller telescopes in La Palma. So I think that he's written a kind of very brief OBS-Anycam package, which you can find on GitHub for getting started with creating your own OBS package. And I mean, certainly it has been a lot of work. I mean, it's what we've been doing for 2 years, but I think, you know, you should be able to get something produced relatively quickly if you look at the OBS-Anycam example. And I think that the DM team is possibly going to put more work into helping other teams create OBS packages. But I think possibly our example, OBS Vista, along with OBS-Anycam, yeah, we're probably sort of key external groups that have tried to do that. And I could certainly talk to you in more detail about some of the issues we had with doing that, if you'd like.
Okay, thank you.
There's also a question in the chat by Matthew, who was asking how comparable are the Vista and Rubin Z and Y passbands, and how easy would it be to identify AGN which vary significantly between the VHS and Rubin epochs?
So have I got an image comparing the two? I think I possibly don't have an actual image in these slides comparing the two bands. They are significantly different. I think sort of broadly the Vista Z and Y bands are slightly wider. So we're looking at now for photometric redshifts. You know, in theory, you do have constraining power from the sort of marginally different pass bands. But I think that you're also possibly in danger of over constraining that part of the SED. So I think that's sort of a matter of ongoing work, really. I think that's all I could say there. Sorry to be a bit vague. They are different. The Vista bands are wider. And I think there's definitely information there. But there possibly needs to be a bit of care taken with, you know, particularly with the calibration solution. I think there, if you've got get some minor differences in the 0 points, you could end up over constraining fits, is my concern.
Okay, thank you. Well, there is another question by Amanda. It's very quick. VHS does not, okay, no, it's not a question, it's a comment. So you can read it yourself. And Franz, super quickly.
So that's quite a key point. Yeah, VHS doesn't have Z and Y. So the very wide area survey that's covering the wide fast deep of LSST, the Vista Z and Y are not available. So it's only available on the video deep fields and the Viking intermediate depth fields.
Yeah, so my really quick question is, do you see actually any benefits of using the LSST pipeline over the original Vista pipeline? I mean, besides putting it on the same pixel scale and whatever, but you know, for instance, background in the near infrared is kind of tricky. Does the LSST pipeline do that better, worse? You know, you didn't show the errors, for instance, as a function of magnitude.
Yeah, so I think that with regard to the background, that's a key reason why we didn't perform the full processing using the LSST science pipelines, and we take the CASU processed Vista imaging with the dark flatten bias correction, because that involves background modeling at that early stage. So I think it's definitely true that the LSST science pipelines are not well targeted to near infrared backgrounds. And that's why we have taken the sort of the measures to use what's already been developed as part of the previous pipelines. With regard to the benefits in the processing, I think that this key feature of the LSST science pipelines is the low signal to noise objects. So in terms of catalog production, I think there's a definite advantage there in terms of being able to produce your own signal to noise cuts on any band, which was not possible with the previous catalog processing. But with regard to the imaging itself, I think the hope is that we're producing the same quality. I don't think we're trying to go beyond what's been done by CASU. Essentially, you know, there's been 20 years of software development by Mike Irwin and others at CASU. So I think the idea is we're aiming to match it by ingesting these slightly later products, but not reproducing all of the aspects of the image processing pipeline, particularly with regard to the background.
Thank you. Thank you, Raphael, for your talk. And let's move on to our last speaker for today, who is Mark Lacey, talking about the host galaxies of low redshift quasars identified in the VLA Sky survey. Mark, we can't hear you. I don't know if you're talking.
Sorry, that's what I'm muting.
You were? Okay.
So yes, I want to start off a little bit about talking about the VLA Sky survey.
Okay. Okay.
You know,
Please go ahead.
So this is a new survey we're doing with the VLA, which covers all the sky north of declination -40. So there's still, although the VLA is a northern instrument, there's still a large amount of overlap with LSST. We'll be observing in 3 epochs, 32 months apart. We've done our first 2 epochs already, and it's at 2 to 4 gigahertz, medium depth, sort of 150 microjansky. But the good thing from the point of view of LSST is that it has a 3 arcsecond resolution. So it makes, compared to most radio surveys, which are a lot larger beam, this gives us very nice resolution for the easy identification of optical infrared counterparts to radio sources. And all the products are public, following quality assurance and archiving. So go take a look at that if you haven't already. And we're also having a science meeting in September in Cicco, New Mexico, but it's a hybrid meeting as well, so you can join virtually. And registration is still open until the 1st of August. So I encourage anybody who's interested in the survey and some of the science we've been doing to attend that. So one thing we wanted to do with this was to do a quasar survey. Because it's pretty much an all-sky survey, it just misses the very south celestial cap. We had the idea of combining with Gaia to complete a census of the brightest radio-detected quasars in the sky. So we're just looking at the bright Gaia sources. The basic idea that if they're stars, then Gaia would have measured a proper motion for them, and we can eliminate them from our candidates when we do a match to the radio. So of course, a lot of these, because they're bright quasars, a lot of these are known objects. About 30% of them, sorry, 70% of them have redshifts in NED, but about 30% of them don't. So we're completing that at Lick Observatory with Eleanor Gates' PI. And later we'll go down for the southern objects to southern facilities like Gemini South or SALT. So it really has worked extremely well. We are better than 95% reliable at finding quasars without needing to apply any optical color criteria. So we can use this to find quasars pretty much everywhere, including in the galactic plane and including moderately reddened quasars. So the advantage of doing a really wide area survey is that we can find objects with quasar luminosities at pretty low redshifts. We can just a little bit above 0.1. And so this means that host galaxies sort of become practical to do, even with ground-based data. 1 + 10⁴ surface brightness dimming makes conventional quasar host work at redshifts greater than 1 very difficult. So this is why you need HSD, JWSD to give you the fine PSF, so you can get into the middle where the surface brightness is higher. And your samples are typically limited in size. So by doing this wide area survey, we can detect faint extended features well away from the quasar nucleus, resolvable from the ground. And of course, you can do this for hundreds or even thousands of objects. So why do we need big samples of host galaxies? So I think it's becoming more and more clear over the past few years that the timescales for significant quasar variability, both in the UV optical and in the radio, are actually much shorter than the traditional idea that it's, the saltpeter time or the lifetime of a large radio galaxy or radio quasar, which tends to be around a few times 10 to the 7 years. If you look at the flicker time scale for AGN, there's Kevin Shavinsky's paper. There's also been a paper by Shin this year, last year, which suggests pretty short time scales, 10 to the 4 to 10 to the 6 years. Really does seem that quasars vary not just by 20% or so, but vary by magnitudes. in a short time scale, so the changing look quasars as well, of course. So, and the other interesting thing that Christina Nyland discovered a couple of years ago, from VLAS in fact, was that a large fraction of quasars have radio jets that turn on a timescale of a decade. So between FIRST and VLAS, so the 1990s and now. So if you think, if you turn that into a lifetime by taking the ratio of the number of quasars in total to the number that turn on, that also gives you a number around 10 to the 5 years. So there's something going on, I don't know what it is, which is setting that sort of a time scale for a lot of quasar activity. Probably the radial loudness comes from the accretion rate variability. It's the idea that from galactic binary sources that you see where you see state changes happening quite quickly related to the accretion rate variability on timescales of months. It looks like the radio loud and radio quiet quasar population may have something similar going on, but on timescales of 100,000 years or so. So the problem is that if you're just taking a small sample of quasars and looking at their hosts, you don't know whether these a given quasar is in a flare state, in a high state, or whether it's an off state when you observe, and that gives you noise in your observed trends. So really just getting a large sample is pretty important. So key to resolving hosts is not just the small PSF then, but also surface brightness sensitivity. And we did this little study that I'll talk about with pan-stars and the NOAO legacy survey, which is a little deeper than pan-stars, but not covering as much sky. The idea is, though, with Rubin and LSST, we could go, we can go significantly deeper and with high image quality as well. So this is going to be a really powerful technique, I think, for looking at quasar hosts. And HSC data, so hypersuprime GEM data have already been used for this. A paper last year by Lee et al. Modeled a host of 5,000 SDSS quasars between redshifts of 0.2 and 1. So on the right, here's just a couple of pictures. So most of our quasars actually have very uninteresting radio morphologies. They're point sources, but you see some with the classic double morphology there. So the focus of our VLAS-based quasar host study was to look at the host luminosities and morphologies of candidates at redshifts less than 0.2. So typically quasars and Seyfert 1s, looking at their host properties as a function of radio and optical luminosity and radio loudness. This was a summer student done by one of our summer undergraduates, Diego Garcia at Middlebury. He's an excellent student. Unfortunately, he has left astronomy at least temporarily, but if he comes back and wants to do a graduate study, he's an excellent student. And his emphasis was to obtain basically quick, mostly non-parametric measures. So here's what our sample looks like in the redshift luminosity plane. So you can see that, yes, there are a lot of Seyferts at fairly low luminosity. This is the approximate dividing line between quasars and Seyferts. Just give you a calibration. So when you're getting out to 0.1, there's a fair fraction of true quasars, but we're also going right down into the Seyfert luminosities. And here's the same plot for radio luminosity. So we are going down. With VLAS, it gets you actually deep enough at low redshift so you can get well into the radio quiet population at the faint end. And also, because it's a large enough survey, we have a fair number of pretty radio loud quasars as well. So one thing we did was just look at the morphologies versus optical luminosity. So you see here that the elliptical fraction rises with luminosity. The tidal features and merger fractions seem to peak just a little below the quasar's Seyfert luminosity cut. So probably, this is the case that we're looking at secular processes at low luminosity in the Seyferts. What's going on at high luminosity, though, is a little less clear, why we're getting a larger fraction of not very interesting host galaxies, and the interactions seem to peak at intermediate luminosities. In the radio, again, we see a high elliptical fraction at high radio luminosities. You have to go to the radio quiet objects before you get a significant number of spirals. So this is kind of known before, but it's interesting to see it in a large sample like this. and then the tidal tails are declining as well. But the merger fraction seems roughly constant, so I would say there's slightly more the mergers of the radio louds. So the non-parametric analysis that we did an asymmetry measurement. We just flip the source, subtract it, and divide by the total flux. We did the Gini coefficient. So the Gini coefficient actually gave us our most interesting results. So the Gini coefficient is a measure of the clumpiness of the light distribution. It actually comes from economics, where it's how much money, what the distribution is of wealth in the economy. So if you've got a few people making a lot of money and not many people making much money at all, then you get a high Gini coefficient. And the same is true of our quasar hosts. If you've had a few pixels containing most of the flux, then those give you a high Gini coefficient. A smooth distribution of flux gives you a low Gini coefficient. And we also did a second moment, but that wasn't all that useful because we had to mask out the center of the PSF because we weren't modeling it. The interesting thing we found when we did a principal component analysis to find out what the strongest trends were was that the Gini coefficient is an extremely dominant in this analysis, both for the radio and the optical luminosity. So what we're seeing is that the radio luminosity is higher for smoother objects, low Gini coefficients, and the same is true to a lesser extent, but still pretty significant for the optical luminosity. So this was a pretty interesting result. So smoother hosts are more luminous in both the radio and the optical. It's sort of quantified as the Bayer application classification of these hosts as mostly ellipticals. So I'm going to talk a bit as well about the Liadel hypersuprime study. So I wasn't involved in this at all, but it was an interesting complement to what we'd done with the VLAS hosts. So they were doing actual fits to the host. They weren't looking at the non-parametric thing. So they were assuming smooth hosts to begin with and fitting models, but they fit 5,000 models to Sloan quasars between redshifts of 0.2 and 1. And so the ensemble properties are well measured. And again, because any individual source is not going to have a great model because it's ground-based data. But if you combine 5,000 of them and calibrate them using HST images, then you can do extremely well. And their basic results were that the rest frame UV colors indicate that about 70% of the hosts are star-forming galaxies, and they tend to be low ellipticity with low Sersic indices. So that sort of tells you that they were face-on disks. Typical sizes were smaller than non-quasar star-forming galaxies, but larger than quiescent galaxies. So again, there's by building up the numbers here, you can build up a picture of the population. So this is kind of an interesting, it's slightly different results from what we're finding in our VLAS quasars, but I think some of that is the radio selection. I think excludes a large fraction of the spirals, this galaxies. So I think these are perfectly consistent studies, but it's really early days for this field. And I think, this is why Rubin is needed. We can get the very large samples with very good image quality and also over a large fraction of the sky. So you can get the bright objects at low redshifts. So basically my point is, I think that we can do quasar host galaxy studies very effectively using ground-based data, probably after about a redshift of 1 with Rubin and LSST. We're seeing that the VLAS quasar sample shows the potential for using large samples to understand trends with AGN luminosity in the radio and the optical. The Liadel paper showed that you can actually fit meaningful hosts out to moderate redshifts using ground-based data alone. And the key advantage of using ground-based over space-based studies is that you can study much larger samples of objects to pin down statistical trends, sort of like climate versus weather. So when you're looking at an individual object or just a small sample of objects, you don't really know whether your objects are flaring or not. But but by looking at a large sample, you can beat down that kind of noise. So that's why I'm finished. Thank you very much.
Thank you. Thank you, Mark, for your talk. Any questions? Well, I see we are also a bit ahead of time. So if there's no question, we might move. I mean, we merged this into the discussion and we started earlier. Okay.